Yeah. Okay, good morning everybody. Let's begin now, I guess. So welcome to the second summit on security and privacy in future mobile network, SECURENET 2024. My name is Bart Chiniarski, and along with the NetSlab team, UCD team, Connect and Confidential 6G project guys, we'd like to welcome you today. Go to the next one. What you can expect from today's talk, or a series of talks, is topics like explainable AI for 6G, in which a lot of our PhD students here at University College Dublin are working on at the moment, trust establishment in data, and a lot of 6G, but also 5G focused topics. Then we'll heavily discuss security and privacy issues and some potential solutions to it, such as federated learning systems or distributed federated learning systems. And then we'll talk about privacy, ethics, and in general, cybersecurity solutions in machine learning. As for last year, which was our first conference, we had about 60 in-person participants, about 150 online participants that signed up, probably around 100 showed up. So in total we had close to 200 registrations and attendees. As for this year, we already have quite a large number of people that have joined on Zoom and YouTube, and people are still coming in to our face-to-face meeting here in UCD. So we hope that this conference or this summit is going to be long-term, and we'll be welcoming you next year as well. As for the day, it's split into 3 sessions. We have our morning session that will start now and continue until 12:30, during which we'll have a number of talks, starting with Lois from Telefonica, and then actually I'm talking about technical talks that we can expect. So we'll have Vera first talking about confidential 6G project that is at a very advanced stage at this stage. Then we'll have Telefonica, a short coffee break. So the coffee area is just outside. As you walk in, you go left, and then it's the main corridor. This is where we will have our poster session 2. Talk number 2 is by Sandra from Queen's University of Belfast. And then we'll have Wings and Nokia. During the lunchtime, which is also going to be in the main corridor there, we'll have our poster session. So we can expect anywhere between 14 to 16 posters that are mainly by UCD researchers. So I do advise you to go there, talk to our students, and ask them a lot of difficult questions. I'm sure they'd be happy to answer all. When we come back from the poster session and lunch that is provided to you, we'll have Engin that is also involved in quite a lot of our UCD projects from CTCC. We'll then have Julian, a PhD student from Germany that is going to be talking about his research work. And then we'll have Madhusanka giving an introduction to the NetSlab and our team here in UCD and what we do, and some ongoing projects. After which we'll have another short coffee break, and then end up with panel discussion, which is going to be led by Drasko. As for people joining online, especially students and other attendees that may be interested, we are going to be issuing a certificate of attendance. So you can expect that it will go into your email right after today. And of course you can use it in your CV in the future if you want to. So that's it for me. I'd like to welcome you again. I can see people are still joining. And now I'd like to welcome Professor Liam Murphy, that is going to introduce School of Computer Science here at UCD. So I'll just put up your slides, Liam. And full screen. Thanks. Yeah, just
Okay,
yeah.
good.
Okay, thank you.
Thanks very much, Bart. Morning, everybody. You're very welcome to this summit. I was here for some of the first one, so I hope you have as good and as productive a day as we had then. So as Bart said, my name's Liam Murphy. I'm here in the School of Computer Science at UCD. So the university was founded in the middle of the 19th century, 1854. But I'm going to give you a more personal history based on my connection with UCD. So I'm not going to talk about the history of UCD. So the first period of interest, sad to say, is when I was a student here. So a long time ago, 1981 to 85. UCD was very different. The country was very different. We had only joined the European Economic Community in 1973, so we were still seeing the benefits, the first flush of prosperity and a link and a connection to Europe that was not really there before. So anyway, in the early 80s, I was one of about 10,000 students in UCD. The Department of Computer Science had been set up in the late 70s, so it was very new. It was only a few years old, and it had about 15 academic staff. Most of them did not have PhDs. Most of them were not doing research. It was largely teaching. There was some research happening. Some PhD students had already started, but it was very small scale. And I actually don't know that much about computer science because I wasn't in it. I'm an engineering student. So I was over in engineering with 300, 250 other engineering students, while computer science had a handful of students in their classes. So it was a small operation, but it had gotten started as its own unit. So that's the 80s. So I'm probably the oldest person in the room, but I remember that very clearly. Okay, so the next milestone then is the year 2000. That's when I came back to UCD as a lecturer in computer science. So UCD had about doubled in size, about 18,000 students. The Department of Computer Science was up to about 22 staff. It was actually the first period of sustained growth for computer science. So starting in the late 90s, they started hiring approximately three academic staff per year. So I was part of that wave that came in. And at that time, most of those folks were research active. Most would have had PhDs at that stage. So the culture was changing quite a bit. And also around that time in Ireland, there was starting to be more research funding available. So in a way that wasn't there 10 years before. And so people were starting to take advantage of that, starting to win grants, starting to supervise PhD students and research master's students, and things were kicking off. So it was a very dynamic place to come to. It was a very good vibe here. And that brings us up to today. So the university has approximately doubled again. So we're up to about 38,000 students. We're now a school of computer science as opposed to a department, whatever difference that made. And we're up to about 65 academic staff. So we're one of the biggest schools in UCD. Almost all of those folks are research active to some extent. We have a large PhD student cohort, I think over 100 students. We graduate 30 to 40 PhD students a year. And as I suppose a reflection of how Ireland has changed and become more diverse and more international, almost half of our current academic staff were born outside Ireland and have moved here. So it's a very different picture to the 1980s when Ireland was a lot more homogeneous and so on. So anyway, that's sort of my connection to UCD. So I've been here now for 24 years as a lecturer. So I just want to tell you a little bit about my experience in running a research group. So when I came back from the US, I actually went to Dublin City University, which is, it's like it's DCU instead of UCD, but it's up by the airport for anybody who flew in. And they had set up a telecommunications engineering focus in their electronic engineering school. So I joined that, and along with some colleagues, I set up this research group called the Performance Engineering Lab. So the idea was to focus on telecommunication systems and look at performance issues in those systems. So initially we were mostly about multimedia networking, and we were focused on, you know, not just the internet, but ATM. So this was, you know, asynchronous transfer mode. This was small fixed size cells, you know, lots of them streaming through the network, different classes of service. So it was a lot of people thought that was the future. But of course the internet had already started, you know, gaining ground, and lots of applications running on it, and eventually won out. We looked at things like adaptive video streaming. So as the network gets more congested, you back off. As the network gets less congested, you can send at a higher resolution or whatever. Adaptive voice over IP playout was very exciting, and so on. And we branched out into other kinds of systems. So component-oriented software systems, these large enterprise systems worth tens of millions of dollars or euros, and how can you, you plug them all together, how can you say anything about the performance of those systems? Will it be acceptable? Will it be good? And so on. We also started looking at mobile and wireless networks, mainly wireless, I have to say. Looked at the various flavors of Wi-Fi, WiMAX, if anybody remembers WiMAX. Not a whole lot on the mobile side. So we branched out into those areas as well, but the focus was always on performance. So not just getting something working and checking that it's correct, but making sure it works well, making sure that, you know, it's fast enough, or it fits in a small enough memory, or whatever it might be in terms of what's critical for performance, and always looking at the end user's perspective. So QoE is the quality of experience. So the idea is that networks and systems and so on, they don't exist for their own sake, okay, despite what some developers might think. They exist to satisfy customers or clients or end users, whatever you want to call them. And it's really hard to make everybody happy, because they're very diverse. People have different expectations based on their history or just their requirements, and yet you have to try and satisfy everybody and make them happy. So that was a kind of a common thread through all of our research is, yeah, but what does the user want? And are they happier now that we've done something? And if so, how can we show that? Despite the focus today, we always drew the line at security and privacy. So in other words, for the first 10 or 15 years, we resisted any temptation to go into that area. I suppose mainly because it wasn't really our background, and you have to draw the line somewhere. So we sort of felt, well, we don't really know anything about it, and our focus is on performance, so let's not take on anything to do with security. So we kind of left that alone for a while. However, you can't resist it forever, and over the last 10 years, I have found myself getting involved in projects like this. So looking at privacy preserving data publishing and looking at value generalization hierarchies within that, looking at metadata leakage through cloud applications, and looking at oblivious servers that might be able to hide access patterns and so on, even from themselves. Looking at anomaly detection in IoT data, and there's lots of possible machine learning approaches you can take. Which ones are likely to work best, depending on your data, and even something like NFC and trying to combat relay attacks. So, through a combination of your research interest change and the people you're working with change and the funding changes, I kind of got interested in areas like this. And I find myself saying a lot, but I'm not an expert in this area yet. So, but anyway, be that as it may, we've gotten involved in that. So I suppose, let me just finish by just telling you some of the things I've learned and some of the lessons I've learned. The first one is that research focus evolves. So I know that, when you meet today, you're very focused on what's going on at the moment in terms of the projects you're working on, the technology, but that will change, inevitably. We're in a very fast-moving field, and if you fast forward 5 or 10 years, things will have changed. The regulatory environment may have changed, the business environment may have changed, the customer expectations may have changed, and so on. So the challenge for us is to evolve our research interests and our focus and our efforts. And it's not always easy. And you probably will, like me, end up saying a lot, but I'm not really an expert in this. But the idea is that we're somehow able to track these changes and still make a contribution. The second one is, I suppose, how important it is to be aware of what the industry is doing. So not being driven by them, not being driven by sort of short term, but here's my pain point today. Okay, well that's an industry problem. But to be aware of what those problems are and what kind of issues and what directions do people in industry think that they're headed in and so on. So all of the work that we did over that 20 or 25 years was in collaboration and in communication with industry. And then finally, the last comment is, from my point of view anyway, the end user experience is the most important. So you must always keep that focus on, yeah, but what does the client want, the customer, and is what we're doing making their experience with this system better? And if not, then maybe have a rethink about what you're doing. So just a few things that I've picked up over this 25 years. So anyway, again, I want to welcome you to today. I hope you have a very enjoyable and productive day today. So thank you very much.
Thank you, Liam. So now we'd like to welcome Associate Professor Madhusanka Lianaga. Madhusanka is running the NetSlab team, and he is also the Director of Graduate Research here at UCD, and he will give an introduction to our group. Okay, and just
okay. Good morning, everyone. So, welcome everyone for the second session, second summit on SECURENET. So we were running this program for the second year, as Bart has mentioned. So I thought giving a basic introduction, like what is this session is about, so the summit is about, so what is the 6G security and what kind of things we need to look into when we are talking about the 6G security, to give a very high level introduction about the talks which we are going to have during the summit, and also introduce a little bit about our research team at UCD, especially the NetSlab research team. So one of the main organizer of this SECURENET event. So this SECURENET event actually jointly organized by NetSlab research team, which is our research team at UCD, and a Connect Center, which is also a research project in Ireland, and also the confidential 6G project, which is Horizon 2020 project. So today's theme is about the 6G security. So when we talk about 6G security, so we have to talk about like how the mobile network security landscape has been evolved throughout the different generations. If you look at the last 3 generations, like 4G, 5G, and 6G, the threat landscape has been evolved a lot. So if you look at 4G mobile network, so where we introduced all IP-based communication for the first time. And also we were having a stable internet connection during the 4G era. And also we were using more and more powerful mobile devices. As a result, when we look at the 4G mobile network, we were more talking about the mobile based attack, and also the applicability of the internet-based attack like APT attack or DOS attack become a bigger issue in the 4G network. From 4G to 5G, the main difference happened is the introduction of the network softwarization techniques like software-defined networking, network function virtualization, cloud computing. So those kind of technologies integrated in the 5G network. So we were facing a new set of attacks related to the virtualization. And not only that, the 5G is going to interconnect a lot of IoT devices, that it is going to interconnect different critical infrastructure. So we have to protect the critical infrastructure via the 5G network. So that also another threat landscape we need to consider in 5G. So what happened when we go beyond 5G? What is happening in the 6G? 6G is also going to introduce a new set of technologies like AI and machine learning, blockchain, or quantum computing, visualized communication, terahertz communication. So there are many new technologies going to be integrated in the 6G network. So we will have a new set of security attacks. Especially we are now discussing about AI-based attacks or quantum-based attacks. So those kind of attacks we need to be considered and solved in the 6G era. So when you talk about 6G, like one of the main difference compared to the 5G is the AI integration. So 6G is I would say like a network AI. So if you consider like today's 5G network, so we have AI integrated very few applications. But when we go to the 6G domain, the AI will be integrated in the whole ecosystem, including from the users to the 6G network itself, and also almost all the applications will be AI domain. So that means when we have considering the security of the 6G, the AI security has to be considered, and it is going to play a bigger role. So when we talk about the AI for security, actually we can consider about the two different scenarios. Like one scenario is like how we can use AI for the security. So that is something we are now heavily looking at in our research project. For example, AI can be used to design autonomous security systems. We can use like distributed federated learning kind of scenarios in order to enable the privacy protection. And also we can use AI for predictive attack detection, or advanced anomaly detections can be also designed with the support of the AI. But also we have to consider the negative impact of using AI at the same time. For example, like the attacks which are targeting the AI system, maybe like data poisoning attack, model poisoning attack, adversarial AI attack. So we have to consider like what is the security impact of using AI, and we need to address it. And also we have to consider the privacy related attack, maybe inference attack, backdoor attack. So there are many attacks which are possible in the AI system, and we need to address those things if you are going to deploy AI in the 6G network. And another thing when we are integrating AI is into 6G network, we have to consider where we are going to use and how we are going to use. So we know in the 5G actually we have introduced the concept of cloud edge computing. So that means we are bringing the cloud computing already at the base station. When the popularity with the AI and the development of edge computing allow us to integrate AI already at the edge of the network or in the base station. We call it as edge intelligence. So we have the distributed AI which can be deployed in the base station at the very closer to the user. Especially the technologies like Open RAN will support these kind of edge intelligence scenarios. So that will be making our problem even difficult. So now we have distributed AI systems, and we have to protect them if you are going to use in the AI system or 6G network. And another important aspect related to the AI is like how we can make sure these AI systems are accountable and also they are ethical to use. This how we can make sure AI systems are ethical. And in order to do that, we have to understand how the AI systems are working. And also we have to understand or make sure this AI system is following the guidelines and the standards defined by the different regulatory bodies, because we are working on the 6G, which is pretty much standardized domain. We have to make sure all the standards are met by this AI system. So in order to do that, we need to understand how the AI systems are working. In this regard, explainable AI is playing an important role. So we can understand how the AI system can be used, and especially we can understand they are aligned with the rules and regulation defined by the standardization. Not only that, explainable AI is a very handy tool. We can get extra bit of information which is important to define a new security rules or design a new security mechanism which can be used in the 6G domain. So not only the AI, another big area like one of the big research area we are working on the quantum computing. Because the 6G network is going to be deployed in 2030. So, and we are talking about a network which can support the services beyond 2030. So by that time, we might have the quantum computing in the mainstream, so there will be a lot of development related to that. So we have to make sure 6G network are also good enough to use in this quantum era. So that's why because when we have the quantum computing, we know most of the cryptographic mechanism we are using today is not going to be used. So we have to think about how we can design the post-quantum cryptographic mechanism. So designing the post-quantum cryptography is one area of this quantum safe 6G communication. Especially we can design a new post-quantum cryptographic mechanism, or we can look for classical cryptographic mechanism which can be still used in the post-quantum era. Not only that, we can work on the quantum key distribution and also the quantum resistance networking hardware. So those kind of area also we have to investigate and see how we can adapt the quantum safe 6G communication. And also we are now looking at quantum-based attacks, what kind of attack will be originated if we have the quantum computing, and how we can make sure the 6G communication is secured in the quantum era. And another interesting area related to the security, so we are looking at these days in most of the 6G SNS project is like how we can enable the zero trust end-to-end security. Because we are talking about the 6G network where we can have like billions of devices, billions of IoT devices. So the manual security configuration, deployment of security services is no longer possible. So we have to go for more automated security solution, and that's why we are talking about the zero trust integrated or zero trust end-to-end security. Especially AI playing a bigger role in this domain, to try to detect the security mechanism, response to it, and also to deploy the mitigation mechanism against it. So basically it can be enabled with this closed loop automation. As you can see here, that's one of the very important research area and research topic we are working on. And also this zero trust architecture is another interesting area, because when you have like billions of IoT devices, it's not possible for you to manually assign a trust relationship for them. So we have to go for fully zero trust architecture so we can automate this end-to-end security. So these are one of the highlights. So we are working on the different research topics and the different EU projects. At UCD, so the Network Softwarization and Security Laboratory, or the NESLab, is one of the research group mainly focusing on this 5G and 6G security. So in this lab, actually, we are working on the 3 different areas. So one of the area is network softwarization and the security automation. We are working on the 5G related technologies like network slicing and make and SDN scenarios, and see how we can enable the security automation. And the second pillar, we are looking at the AI security and privacy. Especially we are working on the federated learning and explainable AI solution, how we can improve the security of these systems and how we can integrate it in the 6G network. The last pillar is about the blockchain for mobile network. So we are looking at different 6G use cases and see how the blockchain can be beneficial for these 6G use cases. So the NESLab is quite large now. We have about 25 members, and we have two co-directors and 5 postdocs, and about 15 PhD students working under the NESLab. And not all of them are from the UCD. We have the members from all around the world, from Finland, and also from India, and also from Sri Lanka. We have different PhD students who are working at the NESLab. So it's a very global research team. We have members all across the world. And in terms of funding, actually, so we are getting funding from the different bodies. So, but for us, the main funding organization is the European Union. For the moment, we have 3 6G SNS projects running on confidential 6G, robust 6G, and also we have some funding from the Federal 5G project. And apart from the European Union funding, we are getting funding from the Science Foundation Ireland under 2 centers like Connect Center and the MLab, and also we are participating with different projects in Finland as well. So if I talk a little bit about the European project we have, it's the spatial project, one of the projects we are running for the moment. It got funded under Horizon 2020. And this project we are trying to develop a trustworthy AI system. Specifically, we are looking at the applicability of the explainable AI for the cyber security. It's not only about 6G network in generally, so we are talking about how we can enable trustworthy AI, how we can ensure the accountability, privacy, and the resilience of the AI system under this project. And actually, this was the first project which was supported the SECURENET event last year, and we were discussing a lot about like how the explainable AI can be used in the security domain. And then we have the confidential 6G project. I know Vera is going to discuss more about this confidential 6G project in the next presentation. And this got funded under 6G SNS. And in this project, we are mainly looking at the UCD team, mainly looking at the applicability of the blockchain for 6G and also federated learning security scenarios. And the last project we started a few months back is the robust 6G project. So this is also got funded under 6G SNS. And this project is mainly looking at the security automation, how we can enable the zero trust security management for the 6G network, especially integration of the distributed federated learning system, closed loop automation with zero trust architecture. And also we got funded from the FIDAL 5G in order to build a 5G test network at UCD. So this is the planned test bed we are working on. So by the end of this year, we will be having this test bed connected with the FIDAL trial net. So basically, we already have a 5G test network with the Densea Island Densea test network. Apart from that, we are going to build fully open RAN capable 5G test network here. And we are targeting two main technologies to discuss. One is the open RAN and the other one is the blockchain capabilities. And also we are discussing about the different use cases like IoT scenarios. We already started for the spectrum management domain. In addition to that, we are trying to work on the augmented reality VR application and also UAE application, also integrated with this 5G test network. And also we have already discussed having some plans to integrate this test network with the other test bed. So definitely we are going to connect with the FIDAL, that's one of the requirements. Beyond that, we will be connecting with the Open Island test bed, which is part of the Connect test network in Ireland, and also we have planned to interconnect with this Oulu 6G test network as well. So that's it about our research work and the 6G in general, 6G security in general. So thank you very much. So hope you enjoy the rest of the summit with the talk. Yeah, thank you.
Thank you, Madhusanka. So Madhusanka is going to be back after lunch for another technical presentation now. I'd like to welcome Vera Stavroulaki. Vera, as Madhusanka mentioned, is managing confidential 6G project, and she's also the co-founder of Wings. So it's yours. Once I get to the slides. Computer is that slow or your presentation is so heavy on pictures.
I hope not. There are not so many pictures.
So is it, if I just go to
you should just go to slideshow.
That's it?
Okay,
Okay,
great.
for one moment I'll just share it on Zoom as well. This would be this. Share.
Right, thank you. So my name is Vera Stavroulaki, as already introduced. I'm with Wings ICT Solutions, which is an SME based in Greece. Wings develops different solutions for various vertical domains, including both the hardware and the software part. This security and privacy is also new for us, so to connect it also with Professor Murphy's speech earlier. We are not experts in this, but we are evolving. Now, confidential 6G is looks into confidential computing and privacy-preserving technologies for 6G. It is a project under the Horizon Joint Undertaking Smart Networks and Services in the specific topic of secure service development and smart security. It's a 3-year project which started in January last year, so we are roughly at the middle of the project at the moment. The total budget is about 5 million euros, and we have a consortium of meanwhile 14 partners with 4 SMEs, 3 industrial partners, and 7 academic and research organizations from 8 EU member states. Myself, I am the project coordinator, and the technical manager is Drasko Draskovic from Abstract Machines, an SME based in France. To give a bit the overall context of the project, so, okay, we consider that 6G infrastructures must, of course, ensure reliability, trust, and resilience on a globally connected continuum of heterogeneous environments, which is supported by the convergence of networks and IT systems to allow future digital services to flourish. And of course, this increase in coverage and network heterogeneity raises even more severe concerns about security and privacy. So in confidential 6G, we'll look into this vision of 6G systems as a deep integration of emerging AI tools, new hardware components and accelerators, networking functions, computing functions, IoT and edge nodes. And obviously, security needs to be enhanced. In this sense, confidential 6G emphasizes on privacy preservation and enhancing security of sensitive data by focusing on data protection in use, in transit, and at the edge. In use is where confidential computing comes into play. This is an unresolved issue. In transit, confidential 6G looks into enhancing communication protection by exploiting blockchain technology, post-quantum cryptography, and traceability platforms, just to give some examples. And at the edge, we are looking more into identifying approaches that are most appropriate for constrained IoT and edge nodes and devices, as well as federated learning so that data do not have to move from the edge, and thus trust and security is enhanced. Here we can see the project objectives. So the project focuses on 3 main pillars: post-quantum cryptography, confidential computing, and confidential networking. And in this context, we are looking into, first of all, looking into the state of the art, analyzing security threats, and being able to, through this analysis, to identify and specify quantum-resistant security enablers, cryptographic primitives, libraries and tools, both for confidential computing as well as confidential networking, that can be applied in 6G and this global edge cloud continuum. We want to have prototypes, or let's say develop prototypes of these mechanisms for confidential computing based both on hardware and software mechanisms. Design and develop secure and privacy-preserving edge cloud networking that is suitable for collaborative confidential computing orchestration, distributed and federated machine learning operations, and then integrate at least a selection of these developed tools and mechanisms in the different use cases that we are looking into to validate at least as much as possible of the solutions developed in the project. And of course, okay, as an EU project, one important objective is also to have some impact with contributions to standardization, disseminating project results as much as possible, and ideally also exploiting these results either in further research or in the future also in products of the consortium participants. So this is just to indicate the rough structure of the project and some of the areas. So as I mentioned, the three main pillars are confidential post-quantum cryptography, confidential computing, and confidential networking. And there we are looking into different cryptographic enablers, tools, and libraries, trusted execution environments, fully homomorphic encryption, secure multi-party computation, federated machine learning, and so on. And of course, as I said, also the practical verification through three use cases. So the first use case we are looking in is dedicated to predictive maintenance for airline consortia using blockchain-based data sharing platform and federated AI orchestration. The idea here is that if we look into airline consortia, there are a lot of data, for example, related to the maintenance of aircraft. This is a big amount of data through which companies could also get insights on different maintenance issues, best practices, and so on. But of course, they are not really willing to share the data. So this is where, or if they are willing, then all of these security and privacy preservations come into play. So here the focus is really on making sure that if data is shared, it is secure and traceable, and also that federated learning can be exploited to learn on top of the shared data, but also minimizing the need to actually exchange the data itself. The second use case is more focused on telecom cloud providers, so providing a confidential computing platform that emphasizes on privacy preservation, enabling mitigation of different security threats. Here, it's more about cryptographic enablers, hardware platform abstractions, remote attestation handling, and so on. This third use case focuses on intelligent connected vehicles for providing mission-critical services, over-the-air updates, and also exploiting federated learning for vehicle-to-infrastructure communication, again, minimizing the need for data to be necessarily exchanged as is. And here we are looking at different applications, like, for example, gaining insights from the connected vehicles on driver behavior, on upcoming traffic, or again also on predictive maintenance issues that have to do with the vehicles themselves, or also the roads from data that is collected from the vehicles. So one of the key areas, as already mentioned, is more related to this post-quantum cryptography, and the key goal is to produce a so-called confidential toolkit. So here we start first from analyzing security threats in the quantum area, and then from that trying to define toolkits for trusted execution environments and post-quantum computing, toolkit for fully homomorphic encryption and secure multi-party computation, and a toolkit for blockchain and zero-knowledge proof. all of this, as I mentioned in the beginning, the idea is that we have a toolkit with different also best practices that can be applied in 6G networks and this edge cloud continuum that we are envisioning as part of these 6G networks and systems. So at the moment we have already produced a post-quantum analysis report which contains an analysis on the threats and the different tools that are available today, as well as an analysis of how challenges towards post-quantum cryptography infrastructures can be addressed. And the next steps are to progress with the other 3 types of toolkits that I mentioned, which essentially will be a toolkit for confidential networking, for confidential computation, and blockchain. So these address also feasibility aspects of the different that are related to these different toolkits. In terms of confidential computing, here we started from identifying requirements and architectural blueprints for privacy-preserving computation, with the aim to research modern confidential computing enablers, advance as much as possible existing techniques for collaborative artificial intelligence and machine learning and multi-party computations, and enhance privacy-preserving computations on the far edge and constrained devices, identifying, as I said, also what is more suitable for these types of nodes and devices. Here again, the first step, let's say, has been achieved in the sense that we have a first report on the requirements and architecture for confidential computing in 6G. You can see a high-level architecture for privacy-preserving computation that has been derived through this analysis. Let's say with key components focusing on data protection, secure computation, trusted execution environments, hardware security models and modules and accelerators. And then the next steps are going deeper, of course, into the design and development of these individual components, looking into hardware modules for supporting confidential computing, confidential multi-party AI/ML, and embedded confidential computing, so focusing again more on the resource-constrained nodes and devices. In the confidential networking, similarly, we start from the requirements and the architectural blueprints for confidential networking, and then we look more into confidential orchestration aspects, considering also the interplay with confidential computing, and again looking into specifically this edge cloud continuum aspects, remote attestation handling and so on, as well as here looking also into decentralized data sharing enriched with post-quantum cryptography and cryptographic protocols applied to the network layer. And finally, federated AI/ML, focusing on the edge. Again, here we have a report, meanwhile, on where we have analyzed the requirements and architecture for confidential networking in 6G, with some first views on how this high-level architecture for confidential networking can look like, focusing mainly on the confidential orchestration, data sharing, exploiting distributed ledger technologies, federated AI/ML, and post-quantum transport layer security. And this is now where we are going to go into further details. So defining in more details and developing this, let's say, individual areas or components of this high-level architecture. As an example of a technical achievement so far in this area of confidential networking, but also related to the confidential toolkit, there is some work already on the blockchain toolkit part, which has to do with self-sovereign identity with zero knowledge proof, coupled with distributed ledger technology for the management of decentralized identities and verifiable credentials. So there is some first work and implementation on this by Zentrix, one of our partners. This is just, again, a view of the different aspects that we are looking into with respect to validation in the different use cases. I will not go into all of these details, but just to mention that, for example, for the predictive maintenance in use case 1 for the airline consortia, one aspect is also looking into confidential smart contracts and transactions in distributed ledger technologies. In the second use case, which is more for the telecom cloud providers, as already mentioned, one aspect is trusted execution environment abstractions to allow cloud providers to enable trusted execution environments very easily in the cloud. And in the third use case, using, for example, blockchain for ensuring security and tamper-proof of shared models. Again, as an example of work that is ongoing in the, with respect to validation, we have also a first implementation of federated learning applied to deriving insights on driver behavior and upcoming traffic. And for demonstration purposes, this is accompanied by such a UI where we can have a view on different parameters that can be collected from the vehicle OBU, for example. Indicative references, of course, a point to start with is the project website. There you can find information on public deliverables. Download the public deliverables. This is a list that is corresponding also to the first results that I was mentioning before. The latest deliverable, secure decentralized data sharing, will be actually available at the end of June. But the other three are already available and can be downloaded from the website. And yeah, this is also just a link of indicative papers. Further available papers can be also found on the project website. Thank you very much for your attention.
Thank you, Vera. I'm very happy to see that the project was a success and it's almost over. So now we'd like to welcome Luis Munoz-Gonzalez. Hi, Luis. So Luis is a senior researcher at Telefónica based in Barcelona, Spain, and his talk is titled Detection and Mitigation of Poisoning Attacks in Federated Learning with Adaptive Federated Averaging. Here. Okay.
Thank you very much.
Thank you, Luis.
Well, good morning, everybody, and thank you very much for the invitation. It's a pleasure to be here. Thank you very much to the organizers, to the guys from the Nets Lab and Madhusanka. It's a great pleasure to be here at Dublin. So today I want to introduce some of the work that I've been doing on federated learning, more concretely on the security aspects of federated learning and how to defend against certain type of attacks that can happen at training time. So as I assume that some of you perhaps are less familiar with federated learning and AI, I want to give you first a little bit of background about federated learning. So federated learning has emerged as a very important paradigm for training machine learning models in a distributed fashion, so that different participants can collaboratively train a machine learning model without sharing their training datasets. And this is very important and very useful in many practical applications where because of oncoming regulations on privacy or existing regulations on privacy like the GDPR, or because of the nature of the data, participants cannot share the data, so they can leverage federated learning to do it in a private way. There are two main typical use cases. On one side, we have cross-silo federated learning, where we can assume that we have a reduced number of participants that have large data sets. For instance, imagine a set of hospitals that want to build better AI tools for diagnosis, but cannot share the data from the patients. A cross-silo federated learning approach is suitable for this case. On the other hand, we have scenarios where we have millions or hundreds of thousands of participants, for example, using mobile devices, where we can leverage the computational power of those devices without the need of centralizing the data from all those users. And there's actually a success story from Google, which is Google Gboard, is the predictive keyboard that uses federated learning at the core of it. So in a nutshell, federated learning works in this way. We have a server or an aggregator or an orchestrator, call it as you wish, and we have the different clients or the different participants in the federated learning task. At each training round, what we do is the server shares a global model with all the participants in the federated learning task. Then each participant trains the machine learning model locally using their own training data sets. Then, after some training epochs, the participants send back the models that they learn during these training epochs back to the server. So not necessarily all the clients have to send back the model to the server. There are different strategies, but for the sake of simplicity, let's assume that all of them send back the parameters to the server. And finally, with that information, with those new parameters sent by all the clients, the server aggregates the information in some sort of way. Typically, standard aggregation methods includes computing the weighted average between the parameters sent by all the clients. And with that, we have a new global model, a new version of the model that would be shared again with the clients in the next training round. So we would be repeating the same process again and again for a given number of training epochs until the training round, until the model converges. Now that we know a little bit about federated learning, let me introduce you the security problems inherent to machine learning algorithms and to federated learning models in particular. So in these slides, I'm talking more generally about the vulnerabilities of machine learning models. So we can characterize the threat model across different axes. Here I included three main axes, which is on one side the attacker capabilities, the attacker goals, and the attacker knowledge. Given the attacker's capabilities, we can differentiate between two main types of attacks. On one side, we have causative attacks, where the attacker can influence the learning of the learning algorithm in some sort of way that happens during training. Examples of that are poisoning and backdoor attacks. And on the other hand, we have exploratory attacks, where the attacker cannot influence the learning algorithm, but try to evade being detected or to produce some errors on the system without direct manipulation on the parameters of the model. With respect to the attacker goal, depending on the security violation that the attacker wants to achieve, we have integrity attacks, availability attacks, or privacy attacks. And these attacks can range from indiscriminate to targeted attacks, and depending on the type of errors that we want to produce, they can be generic, so the attacker just wants to produce errors regardless of the type of error that is producing, or specific. So I want just some specific errors to happen on the target model. And then depending on the attacker model, we have perfect knowledge attacks or white box attacks, where the attacker is assumed to know everything or almost everything about the target machine learning system. Although this may be unreasonable for most practical scenarios, from the defensive perspective and for red teaming, it can be a nice assumption to model worst-case scenarios. In more realistic settings, we have limited knowledge attacks, and this ranges from pure black box attacks to gray box attacks, where the attackers can have some certain knowledge about some components or some features of the machine learning model, but don't know everything about it. And for instance, in these attacks, we have scenarios where attackers can build a surrogate model in order to compromise a target model, where the surrogate model tries to mimic the behavior and the properties of the target system. In the particular context of federated learning, we need to differentiate between two main types of attackers. On one side, we have outsiders, which are attackers that are not participants in the federated learning platform. So, but still they can do certain things. For instance, if the data is collected from untrusted sources, they can manipulate the training data set of some of these participants to try to influence on the learning process. At runtime, when the model is deployed, as in centralized machine learning, they can try to exploit the blind spots and the weaknesses. For instance, by creating adversarial examples, universal adversarial perturbations, this sort of stuff. Or they may be able to intercept communications between clients and server and infer some properties about the data used by the clients, and perform other types of attacks, like membership influence attacks, for instance. On a more sensitive threat, we have insider attacks, where the attackers are participants of the federated learning task. And in this sense, they can perform stronger attacks. For instance, with respect to data poisoning, they can manipulate a higher amount of training data, or they can manipulate directly the parameters of the model that they send to the server, which is known as model poisoning attack. And they also can attempt to infer some information from the data set provided by the other participants and perform some sort of property inference attacks. But in this talk, I'm going to focus on poisoning attacks in federated learning, so those that are produced during the training of the model. And the difference with respect to centralized learning is that we can have a broad variety of scenarios depending on the number of attackers and the coordination between the attackers. We can have scenarios with a single or multiple attackers that are not coordinated, or we can have more dangerous scenarios where we have colluding attackers. Colluding attackers can perpetrate attacks at a larger scale with higher impact on the target model. They can achieve higher attack success rate. And the most challenging scenario would be where the one where we have different groups of colluding attackers trying to compromise the system. So with respect to the attacker capabilities and the fact that the attackers can be outsider or insiders, on one side we have data poisoning attacks where the attacker manipulates just the training data points used for learning the models. In the case of outsiders, we can expect that they can have less influence on the model because they can compromise less data points compared to an insider. For instance, if a participant is malicious, it can manipulate the entire training data set and have a bigger impact on the federated learning model. On the other side, as I mentioned before, we have model poisoning attacks, where instead of manipulating the training data, the attacker manipulates directly the parameters that sends to the server. In the case of outsiders, it's a more challenging attack to perform because it requires to intercept the communications between the server and the client and perform some sort of man-in-the-middle attack. But for insiders, it's an easy thing to do, so they can manipulate the parameters as they wish, as long as they have access to the training procedure or the software for training the model. And with respect to the potential harm, The most dangerous attacks are the model poisoning attacks, followed by the data poisoning attacks performed by insiders, and perhaps the weakest attack is the data poisoning attack performed by outsiders. Let me give you the intuition about how poisoning attacks work in federated learning. Let's assume that we have a very, very simple machine learning model with just a single parameter, that we're going to call it beta, and we have a scenario with 4 participants. And in this case, let's assume that all of them are benign. So after doing the local training, each of these 4 clients sends back to the server the parameter they learned for beta. And in this case, you see that all the parameters are between 4 and 5. And if we computed the average, we have an average of 4.5 actually. But let's see what happens if we have an attacker that says that the parameter of beta is not something around 4 or 5, but it's 100. Now, if we compute the average is much higher than it should be. So in other words, what is happening here is that the average is not robust against outliers or against the possibility of having an attacker trying to influence on the value of this parameter. And this problem is more complex in the case of standard machine learning models, because here we have just a single parameter. But in a real machine learning model, we have thousands, hundreds of thousands, and now with large language models, we have even billions of parameters for our machine learning model. So it becomes a more serious threat. So we need to resort to something smarter to be able to filter out these attackers or this behavior from outliers. Let me show you a couple of defenses that have been proposed in the research literature. On one side, we have CRUM, which is a function for a robust aggregation function, where for each client, we need to compute the distance between the parameters or the gradients that are sent by the other clients. So we need to compute a pairwise comparison for all the clients. Then we compute a score called the CRUM score, which is the square sum of distances between the closest neighbors, given by those numbers. I don't want to get into too many details, but those numbers depend on how many attackers we assume that we can tolerate, and what is the total number of clients, of participants that we have in the federated learning task. And then we pick the client with the smallest CRUM score. The problem with this approach is that at each training round, we just pick the updates from one single client, which is really suboptimal. So because we are not capturing the knowledge from all the benign clients that we have. There is a way to mitigate this problem, which is using multi-CRUM. It's a variant of the algorithm where instead of choosing just a single client with the lowest CRUM score, we pick M clients with the lowest score. We need to be mindful that M cannot be very, very high. Otherwise, we may be including some malicious participants in our aggregation. But again, it has limited scalability with the number of clients, because we need to compute pairwise comparison, and if we have scenarios with millions of clients, it doesn't scale well. On the other hand, we have coordinate-wise median. So as I mentioned before, computing the mean or the average is not robust against these attacks, but computing the median for each one of the parameters provides a robust estimator of the parameters for doing the aggregation in the server. There are variants where we can compute the trim mean. The trim mean means that we eliminate the most extreme values for each parameter on the upper and the lower bound side. But computing this, again, can slow down the time to compute the aggregation, especially in cases with cross-device settings with hundreds of thousands of users, for example. And on the downside, it doesn't really allow to identify the malicious participants. Now, let me introduce you adaptive federated averaging. That is a technique that I proposed with some of my previous colleagues at Imperial College London. where we try to address some of the limitations of the previous methods. So we realized that we can reduce the computational complexity by computing the similarity for each client with respect to a reference model. Instead of computing the similarity with respect to every single client, we compute similarities with respect to a reference model that in our case is a tentative aggregated model that we compute at each training iteration. Then we rely on the assumption that the similarity value for the benign clients should be somewhat similar. And that allows us to identify malicious clients. And we can block that clients that's consistently send bad model updates to the aggregator. Let me show you a couple of examples of how adaptive federated averaging works without going into the mathematical details of the algorithm. So let's assume that the client send the parameters back to the aggregator. Then we compute an aggregate model and compute the similarity of all the clients with respect to this aggregate model, which takes linear time to compute. Then we have the similarity values, which is a single scalar. We can compute the Euclidean distance, the cosine similarity. And then we compute the mean, the median, and the standard deviation of these similarities. So the median is depicted in blue, the mean is depicted in green, and the yellow interval is given by a scale version of the standard deviation. We have a parameters that gives some slack on the uncertainty about this similarity. So based on the standard deviation, we can make it a bit bigger or a bit smaller, depending on how strict we want to be with the detection algorithm. So what we do is the following. We look at the position of the mean with respect to the median. In this case, the mean is higher than the median. So we're looking for model updates that are influencing the model in a negative way and are trying to increase the value of the mean. And we're looking for those values or those clients that have a similarity value outside the interval depicted in yellow on the right. And we found one malicious client. So we eliminate that client and we recompute the aggregation rule. Let's see what happens if we have different groups of colluding attackers. We follow the same procedure. First, we compute the similarities, then we compute the median, the mean, and the standard deviation, the scale standard deviation. We look at the position of the mean with respect to the median. So again, the mean is higher than the median, so we look to the right. And we look for those updates that are outside the confidence interval, and we find one client. So we eliminate that malicious client, and we repeat the process. We have now these 6 clients. 2 of them are still malicious. So we compute again the similarities, the mean, the median, and the standard deviation. And we observe that the mean now is lower than the median, so we look to the left. And we look for the model updates that, again, are outside the confidence interval. And again, we find that there are 2 clients there, so we remove them. And what we would do is we repeat the process until no clients are removed. Then the other component of adaptive federated averaging is the modeling of the behavior of the clients. For that, we use a hidden Markov model where we're trying to infer what is the probability or distribution of each client sending benign model updates. So we have 2 random variables here. The observed random variable, O, which represents the outcomes at each training round of the detection mechanism that I explained before. So it's a Bernoulli random variable that is telling me the update at this training round is good or is bad. And then we have the variable G, which is the variable that I want to infer. And based on a prior distribution on G0 that I have for each client, and we're using a beta distribution to model that, we can compute at each training iteration what is that probability distribution of a client sending good or bad model updates. And at some point, if we observe that the distribution is very skewed towards 0, so the probability of the client sending good model updates is very, very low, we block the clients and we stop communicating with that client. Let me show you a simple example so you would understand. Let's assume that we have this scenario that we had before with 4 participants and one of them is malicious. Before we start the training, the probability distribution that we have for each client is given by the prior. And with the prior, we put an informative prior, so we don't make any assumptions on how good, how bad the participants are. We could, if we had previous information from previous federated learning tasks, we could include somewhat that information. But in our case, for the sake of simplicity, we assume that the prior for everyone was the same. So with that, we see that all the distributions are centered around 0.5. So the probability of sending good updates is half and half. But as soon as we start doing the training, so the malicious client sends malicious model updates. So when we update the probabilities, for the probability for the good clients shifts to the right. So the mean of the distribution is greater than 0.5, and for the malicious client is less than 0.5. So we repeat that. It could happen that at some point we have some false positives. So for some clients we detect them as malicious for a single model, a single training run. But if we continue the training and the malicious participant sends consistently malicious model updates, at some point you realize that the distribution of the malicious participant is quite different compared to the benign ones. And the score or the average of that distribution skews more and more towards 0. So at some point what we do, following a probabilistic rule based on the cumulative probability distribution for each one of the clients, we decide to block the malicious participant. So with that, we also improve on the communication efficiency because we don't exchange information with that participant anymore. And on the other hand, we also reduce the burden and on the aggregation side. Let me show you some experimental results on some machine learning benchmarks. 3 of them are computer vision, MNIST, fashion MNIST, and CIFAR. We perform different type of attacks, from label flipping attacks to Byzantine attacks and noisy clients. And we tested the standard federated averaging and the robust aggregation methods that I explained before. So what we show in our experiments is that for when there's no attack on the clean scenario, things are okay for all the robust aggregation methods except for multicroom that provides a bit worse results. But especially for the label flipping attacks, what we observe is that the robust aggregation methods are not capable of mitigating these attacks. On the contrary, they are quite unstable and oscillate quite a lot. In the table, you can see that consistently adaptive federated averaging, denoted by AFA, in the tables, perform consistently better and is capable of mitigating the effect of the attacks in all cases, whereas some of the other robust aggregation methods fail as mainly in the label flipping attack. Then about the malicious client detection, we observe that our method is very, very good at detecting the malicious clients, except for the noisy participants, where the malicious participants just add noise to the server, where in some cases, for CIFAR 10, the detection methods is not very good, but to be honest, the effect on the results on the federated learning model are negligible. So the attack has very, very little effect there. So we are just filtering the most harmful attackers, and the results are as good as with any other robust aggregation method. Then, by looking at the computational complexity, we realized that, as we expected, that our method is much faster than the other competing methods. Computing the median or computing the similarity, the pairwise similarity for all the clients as in Chrome is very ineffective. And in this case, we did it with 100 clients. Imagine that you have 100,000 clients. So the difference is remarkable. Some limitations and lines of improvement. So in the scenarios that I showed before, we consider IID partitions. So the data is distributed identically across the different clients. But if we have the heterogeneity, the problem is that the variance of the client similarity increases. Our preliminary experiments show still that we are capable to resist to these attacks, but having more variance means that we have higher risk of having false positives, and it could be more difficult to detect stealthier attacks, trying to be less aggressive than the attacks that I showed before. Yeah, just 1 minute. Then about the robustness against stealthier attacks. Nowadays there are very advanced attacks against federated learning systems, and adaptive federated averaging can be vulnerable to these adaptive attacks or these stealthy attacks. The weakness is that we are looking at the similarity considering all the parameters, and that can be a bit ineffective. The way to sidestep this problem would be to look at the specific layers, and perhaps making layer-wise comparison to be able to detect more targeted attacks. Just as a final point, so hope from this presentation you realize that model poisoning is perhaps the most relevant threat to attack federated learning algorithms, especially during training time, and the robust aggregation techniques are really needed, because standard aggregation is very brittle, not only in the presence of an adversary, but also in the presence of faulty users. But robustness can have a price. So what happens if we have a lot of data heterogeneity in the data provided by the participants? So there's kind of a trade-off between robustness as accuracy. But we think that adaptive federated averaging allow us to come up with, or to overcome some of these problems, allow us to detect the bad model updates, and so detect attackers or faulty clients, and to model the behavior of the clients over time. And also it reduces the computational complexity with respect to other competing methods, which is very nice for cross-device settings. Thank you very much for your attention. Again, it's been a pleasure. I don't know if we have time for questions, but otherwise I'll be around the whole day. Thank you.
I think we do have time for questions, if there are any.
Sorry, yeah, just following up on the, a really nice idea of the distribution shifting. Can you also keep a history? So in other words, if I see the distribution shifting, can I go back and look and see how many times do I think you were, like, or is that too much to store for each?
You can compute that information. Actually, you could have kind of a window. In our case, we consider all the iterations, all the history of the client, but you can also consider some smaller window of the history of the participant. But yeah, you can keep track of at which iteration that each client provided a good or a bad model update.
And then use that as part of your decision.
Yeah. So this is starting, or it tried to be a model with the most general case, but you can tweak it for considering different scenarios. For instance, changing the prior, if you have prior information about the participants, or using smaller windows to model the behavior of the participants more locally.
Yeah, good. Thanks.
Yeah, which can be interesting, for instance, in scenarios with online training.
There's a question there.
I was curious as to whether or not you could have a hierarchical aggregation extension of that sort of idea. So if you're doing the aggregation, particularly maybe in one location, and you've got models training on multiple devices, but as the complexity and the number of models increases, then you would need multi-hierarchy sort of things in order to aggregate. And I was just wondering how the complexity of the algorithm that you're currently using would respond to that.
Yeah, actually, that's a very, very good point. We haven't looked into that yet, but that's a very, very good idea. There, I would say that it's also related to the amount of trust that you have in each element in the hierarchy. So perhaps you can assume that at a lower level, you have more untrusted devices, that as you progress higher in the hierarchy. And perhaps you can leverage that to tweak or to adjust how strict you are when accepting or rejecting a model update coming from one entity at the hierarchy level. But indeed, it's a very, very good idea, which is especially relevant nowadays for many cross-device settings. Yeah.
And another question is that, so in a heterogeneous data environment, so models have different knowledge about different circumstances, which may mean that they are giving a suboptimal solution to this particular problem because they're training a different data set. So if the model is perhaps trying to move towards some sort of global minimum, which with respect to its own data set, it's going to try to move there, whereas you're saying, no, you're missing the local minimum of this particular data set. That's what you're doing wrong. And I was just wondering if you have any comment on excluding experts that are looking at the problem in a totally different way and confusing them with malicious actors.
Yeah, that's the main challenge with robust aggregation, that you have this trade-off between robustness and accuracy, especially for capturing the novelty of some model updates provided by participants that may have very, very good insight about some data points. And the problem is that if those updates are quite different from the consensus or from the general consensus from the other benign participants, it's quite likely that you identify that as an outlier. So it's the trade-off that you have, and it's very difficult to come up with a solution that allows you to detect what is a genuine novel update or what is a malicious update, especially when you deal with the more targeted attacks. So it's one of the downsides of robust aggregation. You need to take into account this trade-off between robustness and accuracy. So there's no free lunch here.
That's where some prior information might come in handy as well. If you knew that.
Yeah. You could use that. Actually, that was our idea of building this reputation score with the clients, because you can use that for those type of corner cases. Yeah. So yeah, perhaps it's a solution. But if you think of smart attackers, they can try to evade that by building a good reputation, and they performing the attack.
Yeah.
So it still is challenging.
Hi, you mentioned a layered approach rather than parameters. Can you touch more on why would you prefer layered?
Yeah, because you reduce the dimensionality of the problem. So instead of computing the similarity with respect to millions of parameters, you just compute the similarity with respect to 100. So the similarity value that you are going to get is perhaps more informative. And you can think of that, for instance, for detecting some backdoor attacks that tend to operate more in the final layers of the machine learning model. So you can look specifically at that. But the problem is that if you just do that, maybe the attackers can leverage the weakness of your model and try to influence more on the earliest layers. But the idea is try to reduce the dimensionality and find more local analysis of the variations of the model across layers. So that helps to detect more subtle attacks. But how to coordinate or how to do a whole analysis of taking into account the similarities with all layers, it needs to be taken carefully.
Luis, we also have one online question, and it goes as, could this adaptive federated averaging method that you presented, can this be applied to decentralized federated learning scenario?
Do you mean what type of scenario? Peer-to-peer?
Hard for me to say because I'm just reading the question
Okay.
on Zoom. So I guess he's just asking more about the decentralized,
Yeah.
as opposed to.
I guess that you could apply this to, for instance, to peer-to-peer learning, but there each node, each participant in the peer-to-peer learning task should have or should build its own reputation score for all the neighbors that are connected to that node. It can be applied for that type of settings. The other setting that would be interesting to use is the hierarchical federated learning that we mentioned before, and actually it's a good idea to evolve this work. Yeah.
Okay. Thank you so much, and that brings us to our coffee break, which is scheduled now for half an hour, and we will be back at 11, if I'm not mistaken, with Sandra's second technical talk. Thank you so much, Lois. Thank you. So the coffee is just outside in the main corridor near the poster session. we're smoothly transitioning to the second part of our conference, and I'd like to welcome Professor Sandra Scott-Hart from Queen's University of Belfast. Sandra will be giving a talk on exploring secure, intelligent, programmable, not too sure how to pronounce the abbreviation SAGINs, but essentially it's a space, air, ground integrated networks, and the stage is yours. Again, if you have any questions, we'll keep it until after the talk.
Okay, good morning everyone. Thank you for the introduction work, and to Madhusanka and NetsLab for inviting me to join your conference this morning. So as mentioned, I'm going to talk about secure space, air, ground integrated networks. But I thought first, I'm expecting that many of you aren't familiar with Queen's and our cybersecurity research, so I thought I'd just begin with that. So I'm an academic at Queen's University in Belfast and doing my research out of our Cybersecurity Institute, which is the Centre for Secure Information Technologies. So we're the UK Innovation and Knowledge Centre for Cybersecurity. The other interesting aspect worth mentioning is our Cyber AI Hub, which probably links in a lot with the topic of the summit today. So the Cyber AI Hub was launched last year. It's a multi-million-pound project working with cybersecurity and AI companies. So essentially our model is, within CSIT as an institute, we have sort of our academic research, and we have an engineering team that helps to bring that research to reality. And we work very, very closely with companies, and as Liam mentioned this morning, obviously looking towards the impact of the research, and the industry and the end user focus is really important for us, and indeed for everybody in the research space. So with the Cyber AI Hub, we have specifically 8 companies that we're working, or 8 projects that we're working on. And I lead one of those on Open RAN security. But we work with a model where we have the academic team within CSIT, we have engineering from CSIT, and then we have engineering and leadership from the company. And we've got 8 of those, and the idea of these projects is to look at solutions either using machine learning and AI security within company technologies, or helping them to protect the use of ML and AI technologies. So that's that piece. In terms of the background to my work, I've been working for over 10 years really in software-defined networking security. So as we've also heard this morning about the use of security and then the protections against security threats. So we've done the same thing with SDN security. We looked with, so software-defined networking being the idea of separating the data and control planes in the network, introducing programmability, and giving us a global network view. So you can benefit or hope to benefit network security using that global network view and the programmability, being able to iterate and individually address security solutions for the network. But also that separation introduces vulnerabilities as well on the interfaces as we separate out and distribute the elements of the network. So I see a lot of similarities actually in SDN and the frameworks we looked at in introducing SDN, hierarchical and distributed frameworks, and the challenges associated to those, and the likes of our Open Radio Access Network and our distributed networks and wireless techniques today. So background in working on that. Also then, as you're more than familiar with machine learning and AI becoming ubiquitous, network security solutions also started using machine learning to accelerate and manage the large scale data that we have in those networks, with the data, with the traffic. So machine learning based solutions, for example, intrusion detection systems, distributed denial of service systems, we started using the techniques to develop better systems. And then we also started looking at, well, this is a security system. We're supposed to be improving our network security, but we're potentially introducing challenges and vulnerabilities to that system by the use of machine learning. And Luis already mentioned the types of poisoning and evasion attacks that we can experience in that space. So we looked at developing the solutions. So for example, convolutional neural network-based distributed denial of service system. So a solution using that, and then generating adversarial samples to improve the design and the training of that system itself. So a bit of work in that space. I mentioned the project, the Cyber AI project, that's focused on security, and we recently published on misconfiguration in ORAN, in the Open Radio Access Network, as a result of the impact of AI and ML use in that space, so for optimization, etc. The challenges might arise there. We've also done a bit of work as a Polymath Fellow at the Geneva Centre for Security Policy for a couple of years, and the idea there really being a couple of mentions, I think, in Madhu's introduction earlier about the legal, ethical and social implications of the use of these technologies, ethics and bias, for example, in our training of certain AI-based systems. So I've looked at the technical work that we do on network security and using AI and bringing that to the population, so the legal scholars and policymakers and government representatives, to try and raise awareness, okay, not just to adopt these solutions without considering what are the challenges to them, and including some of the technical challenges. So this isn't a technical solutions talk. I'm going to highlight just a few challenges and requirements and considerations that might be made as we're developing 6G and beyond. So SAGIN is how I would pronounce it. I don't know if that's right or wrong. Space Air Ground Integrated Network could be Space Air Ground Sea. Non-terrestrial network is a term used by 3GPP, aerial access network, etc. But the main element here is we're integrating all these layers of nodes and services, satellite communications, high-altitude platforms, unmanned aerial systems, and into our ground infrastructure for networking itself. And with that, we get, as you can expect, massive scale and complexity. Also some intricacies that we haven't seen yet this morning, maybe later today, some discussion of as you go higher and go more global with the space system, for example, introducing low Earth orbit satellites, for example, you then talking about these astronomically distant networks, which changes the type of routing and networking required in that space. So also the distance that we experience with that, you're not going to be automatically or easily able to switch out nodes and devices on the fly. There's a cost to launching equipment and the cost to running it and maintaining it. And that has to be thought of both in advance and in terms of the potential, I suppose, an extension of what we already know as self-organizing networks, where machines interact amongst themselves and have swarm-type behavior to enable the communication. And a couple of other things I'll come on to in terms of resilience and trust as we go through this. So a couple of architectures just as a visualization of this. So I mentioned the layers, you've got the ground and maybe the sea network involved, and those platforms. Aircraft can be used to transfer data, operating as nodes within our network. We might have UAV or unmanned aerial system swarms. And then at that space level, we've got the low Earth orbit, medium, and out to geostationary orbit. In terms of space networks. You can see a lot of moving parts here. A second illustration similar on the left-hand side. And what we're looking at now is not necessarily the bidirectional, so an uplink and downlink communication to one or other satellite from the ground, but maybe hops between layers and different nodes that introduce a network. On the right-hand side, you've got an illustration of a swarm of UAVs, unmanned aerial vehicles, cooperating to provide coverage of the ground. And that, as you can imagine, I mentioned already that sort of multi-party interaction and the dynamic nature of that. But you've also got their potential self-organization requirements and the use of, we see the use of machine learning heavily in that space to understand the behavior and make decisions about routes, for example. So some things I'm going to talk about: programmability, security, and intelligence. And something of a personal interest of my own is the sustainability as well. In terms of challenges, there's issues around frequency and spectrum allocation and usage with the increasing number of nodes across the network. You've also got, I mentioned already, the interlinkages between the networks and self-organization, but you've got ground stations and satellites to contend with. In terms of additional challenges beyond what we know sort of as even the low Earth orbit or the high altitude platforms, at the wider distance, you've got different coverage to consider. Obviously, you get more coverage at a higher level or further distant from our Earth. but you also have mobility elements to contend with and difference in the propagation patterns there. So there's a lot of complexity introduced into these systems, but it is a vision of 6G that we will be able to leverage all of these elements to provide a more optimal routing and to enable, again, a point that Liam made about the end user. This will all become invisible to the end user, but there's a lot of complexity layered into offering that seamless experience of delivering communication. So the other thing to consider then is, and I mentioned the software-defined network as an example, sort of leading into this 6G and Open RAN, different elements that we see of the communication design. The idea maybe of the satellites themselves offering a data plane, so becoming the nodes within the network at that level, and what we might need in terms of delivering that. So at that level, considering, I suppose, the differences in the communication patterns there, we have an introduction of delay-tolerant networking. So with mobility, with dynamic nature, and with different patterns of, from a physical layer perspective, even from transmission, we have longer latencies and intermittent connections. We can't always rely on delivery, so we don't use the same routing techniques that we can use on the ground. So for this, the bundle protocol was introduced by NASA, which manages packets and the transition of those in the space framework. There is a secure version of that called BPSec, offering authentication, integrity, and confidentiality. But there's little and limited exploration of that to date. So some of the work we're doing in the team is looking at how this might be applied and bringing some of the programmability and the security to bear on offering, for example, even if you think more closely to Earth, not necessarily looking towards communication with the moon or anything, if we think about disaster recovery scenarios, there's a similarity there in terms of the intermittent connectivity. And we can maybe use bundle-type protocols and secure those to provide a better transmission path. Some of you may be familiar with, again, from STN, P4, it's a programming language. The idea with P4 is that you can define, in fact, your own switch behavior, so routers and access points within our network. We can define how they want to transfer the traffic that they receive on the network. And I think that it's maybe a good candidate for the likes of a newer protocol like BP or any other delay-tolerant protocol that is conceived of that can be designed into these systems themselves. We can write this very simply to operate within the node. And then they could be deployed, as we say, in satellite environments or in any other environment. So we would have software-defined, delay-tolerant network nodes. To be determined, what level that operates, but again, something that we're looking at. But one of the challenges there is with the programmability, we get the flexibility, not only with being able to write our own behavior, our own network behavior, but then we also have the challenge. So in the ground networks, in our telco operators have been quite slow and loath to adopt SDN. It is in place quite predominantly now, but it's been a slow process because they couldn't determine or assure the behavior of the network. So talk about quality experience, but quality of service and the service level agreements that operators have to agree to and offer to their client base. When we have the ability to change behavior of the network on the fly, as happens in a programmable network, so we can offer reaction to events rather than defining the specific behavior. So under a certain circumstance, one action might happen, another circumstance, a separate action might happen. That offers an openness within the network that the behavior is not known necessarily at any point in time, and that's very troublesome for a network operator. So you can imagine if we do want to consider this for a space environment or even a more remote environment, we'll have to counter those challenges as well, and that acceptability from it. In terms of security, there was some posters outside looking at about the idea of the beamforming. That can be a particular challenge or a particular security vulnerability in places. We've seen the use in the Ukraine, the LEO constellations, so the low Earth orbit mega constellations, the likes of Starlink have thousands of satellites in low Earth orbit, offering connectivity across the globe. There's also Telesat in Canada, OneWeb across the UK, with hundreds, and Amazon coming to proposing, they currently have several satellites up there. They're looking at thousands as well. So all of that can offer a great solution in terms of the connectivity in situations, disaster recovery situations, for example, or in this instance. But they're also vulnerable from the security perspective, and not only from a physical security, but so not only at least from cyber, but from this physical security perspective, just from the interruption or the interference of signals can easily take out links within the network. Now there are solutions to some of these, but it does remain a challenge to be addressed, something to be considered. And the second part of that is actually the idea that there is a cost to deploying this equipment. So you have different launchers, certain people have access to the launch platforms, certain organizations are developing the actual CubeSats or smaller form factor satellites. So they will host payloads from other organizations, and parts of the components of that may be delivered by other organizations. They may communicate to different or ground facilities under the operation or the control of different organizations. So there's a lot of elements here from that supply perspective, from that security perspective, consider who actually has responsibility for what, and are you comfortable with deploying, and how you protect your, if you're the owner or the deployer of the satellite, how you protect your system from the instances running on it, virtual instances or hardware running on it. And the NIST, the National Institute of Science and Technologies, are looking more closely into that space and offering recommendations around that. To date, from an intelligence perspective, machine learning and AI is used broadly. Mostly at the moment used for optimization purposes, so management, for example, radio resource allocation and those sort of bandwidth allocation exercises. Luis has already given some detail and background about poisoning and evasion type attacks that can be experienced by machine learning techniques. But in this context, we can think about the security issue from the actual implementation. If you had, for example, the routing being determined by a machine learning algorithm based on the reliability of the links, so you're going to choose which way you transfer the network through your interconnected nodes, based on the reliability and the availability of specific links. That reliability is determined by weather conditions, let's say, and somebody can, malicious adversary can influence those data points and then thereby influence the whole distribution, the whole network routing capability. So it's a similar kind of behavior to a black hole attack that you might have, that we might be familiar with, people removing, offering a denial of service on our nodes, but it's scaled up by several tiers back in terms of where that vulnerability is introduced. So we need to think about the security there. And there is a sort of highlight here, quite a lot of the services and use cases that are being considered and commercialized. So when we think about the security and the protection and any of the design of the satellite services and nodes to date, a lot of that has been done by government and military because they were large at geostationary orbit. We have the likes of the location, position and navigation. That is quite well secured and protected if it's done and designed and implemented by a single operator, such as a government. But commercial operations are now being introduced with this phenomenal number of LEO satellites for all sorts of different monitoring and tracking, video offering, and using different spaces, interesting things like real estate use cases, using visualization of the maps of what's going on, and then for more social activities as well. But basically any of that being interrupted, either spoofed, interfered with, or disrupted, means that you can't rely on the data. So it becomes more interesting from a commercial perspective as well, where there's not necessarily the same emphasis on security. Again, I'll refer back to Liam's presentation. Performance has always come first in design, and security is often left to the last minute, even though we keep trying over and over again to introduce it early. I'll skip over this from a time perspective. But just on to the last piece that I want to mention. So these are some illustrations of how busy the space around Earth is today. So different images of constellations of satellites being deployed. It's getting extremely congested, and although there's some effort and requirement in terms of deorbiting those satellites that you put up there, and mitigating any debris that comes down, or safely removing them from the sky, there's still a lot of work being proposed around disposable and attritable UAVs, for example. So there's a tension there between the idea of managing the space and keeping it clean, and our sustainability goals that we have from the UN, and then the idea of, okay, we can do something and we can do it quickly. I've got this great little toy that will do this particular job. We have to manage sort of our attention to that. So there is a focus on secure sustainability, which I suppose my point here is to promote it more broadly, and to suggest that we might want to think about what we're producing and why, and the benefit of it overall. So just to summarise, the area that we're looking at is obviously the extension beyond just ground infrastructure and near Earth infrastructure out to wider global constellations. We've got physical and cybersecurity challenges there that we still need to do some work addressing, and potentially raise those now in the early stages and try and combat that focus that we always have on performance of our services. Programmability could be a potential, but we do have that tension of the autonomous behaviour and being able to assure that and introduce some new improvements on that. And then obviously we're going to be using machine learning and AI for optimization, and we definitely need to build in some of our solutions around securing that in advance of deployment of those. So thank you very much, and I'm happy to answer if there are any questions on that.
Thank you, that was very interesting. I see you're focusing on the security of the network itself, but what about internetworking and handover between different NTNs? So for example, let me give you an example. In the UK, of course, we have identified high-risk vendors, and we've stripped out a lot of our RAN equipment as a result of it, even going into the IMS core for some. Now, if I'm theoretically, once we have NTNs in full operation, I may hand over from a terrestrial base station to a satellite base station. That's okay in my own network, but when I'm roaming, I have no control over the RANs which are now in space and on land, over which I might pass, and therefore the NNIs between those different providers. Are you looking at that sort of direction at all?
Absolutely, yeah. No, I mean, and I suppose I consider that when I talk about the NTN saga, I'm considering the whole global, and therefore that's the massive complexity of it.
So within that, you have all of these different individual operator ecosystems.
Exactly, and if we're talking about the constellations, for example, it would be the Starlink, handing to, maybe sharing and exchanging with Telesat, and all of those tensions that you have in there. So no, I consider the whole piece to be a challenge, and I didn't have time to include any of it in here, but so the work with the GCSP, for example, Geneva Centre, the particular consideration is on Earth we do have our legal frameworks and our regulation of who owns, what's in sort of near Earth space. But when we go outer, there's no global regulation or legal regulation on who's responsible for what. So that introduces massive challenges as well. So no, absolutely,
it's the HRBs, won't it?
Yes.
I'm wondering if there might be some sort of operator-based policy control to explicitly prevent me from attaching to a particular kind of equipment in the future.
Yeah. I mean, I think there's some examples of when I mentioned the jamming, for example, there's some examples of defences in place so that you can detect a malicious, let's say satellite in this case, approaching, from a physical attack perspective even. So there are different solutions being explored there, but I think, it's a wide open space.
I guess it may be possible for business applications, the consumer world may be a bit different when I'm referring
I'm
to.
thinking only of B2B or governmental applications. information.
Yeah. So hopefully that is, and obviously the problem you're referring to is very well known. Even for this year's some of the H2020 or Horizon proposals, we had to explicitly say that we are not going to use XYZ equipment in any of this work. So we all know about this, and yeah, that is another layer of problems that we are yet to see. Alex?
Thank you. So with regard to the topology of the network, so there's a lot of different components, and maybe there's some predictability about where they will be physically in space. And then you have the changing needs, and then you have threats which act upon the network. So what I was curious about, if you have any guidance with regard to programmability versus autonomy of the various components of the network in order how to route and respond to their own traffic from their perspective within the network, rather than like a global perspective on the network.
Yes, so I think that it actually has to be more along the lines of the autonomous, because of the location of the nodes. So we would never, well, not never, so with, I guess with the SDN, the software-defined network, you have that idea of the logically centralized control, but it's very unrealistic in a real deployment that it can be, one or two controllers. There will always be the multiple. So we think of it potentially as having the nodes themselves are they're operating. You probably have groups of programmable nodes with some hierarchy of control between them, but they would, within the programmable devices, I would consider them to have different options of behavior. So they might not be so broad as to have pure independent decision making, but they might have a selection of options that are feeding in, almost from maybe if you had a digital twin type effect where you could predict what the behavior might be, what the response to the network might be from certain reactions, so that it could be done within the nodes themselves in a more distributed fashion.
Okay,
Yeah.
Thank you very much. Thank you, Sandra. So now we are moving on to our Greek partners again. So we have Christina Karasatou. Are you the only presenter, or is Konstantinos also presenting?
No,
I'll just
it's just
part of this work. Okay. So I'll put it aside for you. Okay. Okay. Thank you.
So hello, and yes, I'm Christina Karasatou. I'm from Wings, and I'm going to present the work that we've been doing with Konstantinos Lesis, my colleague who unfortunately could not be here today. The work that we've been doing within confidential 6G project. And the title that best suits, let's say, describes our work is the process of designing a fully homomorphic encryption scheme to encrypt the information exchanged in a federated learning model. So the agenda of the talk today is first to give you a description of the classification problem that we're looking at, then the classification techniques that we have seen without taking into consideration any security aspects, and the results that we have within classical machine learning problem techniques. Then adding federated learning to add security to our enhance the data privacy in our problem, and then is to see the results that we have in that, and then the fully homomorphic encryption scheme that we see into adapting, and then the conclusions on our work so far. So the classification problem that we look is is related to the use cases that we showed earlier today regarding confidential 6G project. The first one is regarding predictive maintenance for airline consortium using blockchain-based data sharing platform and federated AI ML orchestration, where here the general idea of the project is to build a platform to enable secure data sharing and between airline companies, aviation companies, manufacturers, regulation bodies, and other organizations And the main goal that we look at is to enable predictive maintenance driven by AI and federated learning in order to preserve data privacy. And the other use case, the other problem that we look at is the one related to intelligent connected vehicles, mission critical services, and over-the-air updates with FL and vehicle to infrastructure communication. Again, the bigger picture for this problem within the project is to provide mission critical services within the context of secure vehicle to infrastructure communication, to provide over-the-air secure vehicle system updates with distributed learning. And what we do, our goal is to collect data from connected vehicles in order to develop federated learning models that will enhance road safety and driving experiences by supporting driving decision making. Okay, so these are the two problems that we look at. In this talk, we're going to discuss only about the connected vehicle, but the same work also goes for the airline with the engines of airplanes. No. Okay. Okay. Without taking, like I said previously, without taking into consideration any data privacy, the way to go for that is we chose to use random forest classifier to solve this problem, which is an ensemble learning technique, and it combines multiple decision trees, and this allows us to have higher accuracy and to reduce overfitting, and it's widely used for classification tasks. The benefits, how it works, just a brief reminder of how random forest classifiers work. Of course, they have two phases, the training phase and the prediction phase. In the training phase, we use random subsets of features, they are created and data points, and individual decision trees are built using these subsets. And then in the prediction phase, a new data point is passed through each tree in the forest, and then each tree makes a prediction, and then we take the majority vote to determine the final class label. Why we chose random forest classifiers? It's because they provide high accuracy. Since we have multiple trees, yes, in comparison to single models, it gives have more accurate predictions. This also provides reduced overfitting. Random selection of features and data points during training helps to prevent the model from memorizing the training data, and it generalizes well to unseen data. And also it handles well missing data, and also it's robust to outliers. So the presence of outliers in the data has less impact on random forests due to the averaging across multiple trees, again, as opposed to single model. The data set now that we've used on traffic, driving style, and road surface conditions, it contains parameters acquired by cars via OBD2 scanners. The dataset were collected by 2 cars, and so we have two types of problems. The first one is regarding the traffic congestion conditions, and the other one is regarding the driving style of the driver. So we have, for the traffic congestion, we have 3 classes that at data instance we want to classify it. It's the low congestion condition, the normal congestion condition, and the high congestion condition. And regarding the driving style, we have an even pace style and an aggressive style for the driver. The features that are included in this data set are this list. It includes altitude change, current speed value, the speed variance, the speed variation, longitudinal acceleration, the engine load, engine coolant, temperatures, the manifold air pressure, the revolutions per minute, the mass airflow rate, the intake air temperature, the vertical acceleration, and the average fuel consumption. So all these are the features that are included. So for the classical machine learning algorithm, using a random forest classifier, for the problem of predicting the traffic congestion, the accuracy of our model was 0.9. And for the driving style prediction, the accuracy was 0.83. Now, so this is the simple, the classical machine learning model. Now, moving on to federated learning, so that we enhance the data privacy. Luis previously explained very well what is federated learning. Just a small reminder, it's a decentralized machine learning technique. It trains models on the data that are stored on individual devices. There's no need to upload the raw data to a central server, and this way we have data privacy. So the data are not transmitted back and forth between the parties and a central server. So the benefits of federated learning is that we have enhanced data privacy, like I mentioned. It enables training on sensitive data, so parties do not expose, if they have sensitive data, they do not expose them. It has an improved model generalizability, and because of this, avoiding this back and forth of transmitting data, we have reduced data transfer costs. Now, the framework that we've used for federated learning is Flower. The reason that we chose that framework is because it's flexible and customizable. It supports a wide range of machine learning frameworks, like PyTorch, TensorFlow, etc. It is easy to use. It has a user-friendly API that simplifies the process of building and deploying the federated learning systems. It is scalable, which is we have to take into consideration if we want to deploy many vehicles in our solution. And then it also has rich experimentation features. Now, so the results that we got for using federated learning, again, by deploying a random forest classifier, for the traffic congestion problem, the accuracy that we got is 0.87, as opposed to the classical ML model's accuracy that we got that was 0.9. And then for the problem of predicting the driving style, the accuracy that we got is 0.81, as opposed to 0.83. So we see by adding federated learning, we don't have a big toll on the accuracy. So it is a very small price to pay, let's say, for adding data privacy to our solution. So now the next step on top of that is that we look for is to add on top of that fully homomorphic encryption. And by fully homomorphic encryption, what is fully homomorphic encryption? Is a technique that enables computations on encrypted data. It supports addition and multiplication operations on ciphertexts, and the encrypted results can be decrypted to reveal the original outcome. And what we mean by that is that if we have two integers, x and y, and if x plus y equals z, then encrypted x plus encrypted y, it will equal to w, let's say. And if we decrypt w, then it will be equal to z. So, yes. So if we apply fully homomorphic encryption in federated learning, it will encrypt model updates on the individual devices, and then the model updates that will be performed in the aggregator, it will be on encrypted data. The data will never be revealed, even for the model parameters. And So yes, aggregates encrypted updates to create an improved encrypted model, and then it preserves data privacy even on the devices and during communication. Alas, I mean, it's a very nice and powerful tool, fully homomorphic encryption, but it has a cost. It requires high computational overhead. It has increased communication costs and potential accuracy limitations. So this is what we want to see, because there is a trade-off between the extra data privacy that we have in our solution, but we need to see what is the toll that we have to pay if we add this. So to conclude our findings so far and our next steps, we see that the federated learning model has slightly lower accuracy compared to classical machine learning model. But like I said, like we saw, the difference is insignificant. So federated learning should be preferred when data cannot be shared due to privacy reasons. It can be federated learning. It can be combined with fully homomorphic encryption in order to ensure secure communication between server and client. But it's this is our next step. Like I said, is to see this trade-off, to calculate the computational cost that FHE adds to the model, and also the accuracy, if it has a cost also in accuracy. So I think I was talking fast, and I finished earlier. Thank you.
So do you have any questions for Christina?
Yeah.
Yes, I was wondering, you mentioned that you had two cars that the data came from.
Yeah.
Are those then the two parties in your federated setting, or how many parties did you consider for your experiments?
Yes, for now it had only two, but we want to generalize.
Ah, okay. Yeah, okay. So I was wondering whether you could say anything about how you expect that to scale as the number of parties.
It's it's our. I think, in our view, it won't probably affect the accuracy in a significant manner. Of course, it will. We will have to see them how accuracy goes, but I think the indications that we have is that it will go well.
Yeah, that makes sense. Thank you.
Yeah, thank you.
Alex?
Yeah, so I was curious about the encryption component as a cost, and what I was curious about is like if layer net, like, you know, instead of distributing keys or having a hardware solution, if additional neural network layers could be customized for providers, or say if I'm transmitting data, I have my own layers that in my network that decrypt on the fly, and you have your own layers in your network that encrypt on the or vice versa.
Yes, that's an interesting approach. We haven't taken it into consideration, but yes.
I was just wondering generally what the challenges were in relation to the limiting bottleneck.
Yeah, this is the work that we're doing now, so yes, I cannot say much on that, but it's the computational cost that, for now at least, for what can I say now, it's the computational cost that comes with the noise that you have, that you introduce to enhance the data privacy, and then it depends on the framework also that you're using and the techniques that they offer you, like bootstrapping or anyway. I don't want to say too much because right now, let's say, we're exploring our options, but yeah, we'll come back to you with that.
Maybe a question on the same note that you mentioned, not this computational overhead. Did you experiment with different frameworks for fully homomorphic encryption, and how do they compare? Did you see that some are a little bit better? And also, as a kind of follow-up question, is there a possibility to accelerate this by some kind of hardware acceleration, maybe GPU or, I don't know, some specialized unit? Are there these kind of things that exist on the market, or in the academic maybe experiments?
Thank you. For the first part, we're in the study phase. We haven't implemented it because because there are different options also regarding how generalizable is its framework. So we haven't. We're in the start of the implementation, so I cannot tell much on that right now. And regarding the devices, the hardware acceleration that we could have, for sure it's something that we need to study. But if we look at it on the practical implementation, let's say, is that then we need to ask for the clients to add things on their infrastructure. So for now, let's see, the first step in our view is to see how it, to have a global solution without asking extra from the parties. But for sure, it's something that we need to study because or private data privacy also can be enhanced through hardware, and also the times, the computational times can be reduced using stronger machines, let's say. So yeah, again, I think this is a trade-off that needs to be visited.
This is always calculated on the edge or something that is centrally calculated? I guess
it's on the edge.
On the edge, at the client.
Yes.
Can I understand? It's a big demand, I would say, requirement from the clients too.
Exactly.
Thanks.
Yeah. Thank you.
Okay. Thank you, Christina. Thank you so much. And we smartly move on to our next presenter that came all over from Finland. It's Shushu Liu that is working for Nokia Bell Labs. I'm sorry if I butchered your name and second name, so maybe introduce yourself.
Oh, sure.
And I'll the slides for you. Is it Shushu or is it?
Shushu Liu.
Oh, so it wasn't that bad.
Very close.
Okay. Share. Slides. This is the first one?
Yeah.
Okay.
Yeah.
You want me to move this around, maybe?
It's fine.
Yeah,
I can
work
manage
away.
it.
Okay.
Yeah. Okay, so hi everyone, and it's closing to lunch. I will try to be fast. First, a little bit introduction to myself. My name is Shushu Liu, and I work in Nokia Bell Labs in Finland. My research has been mostly focused on security and privacy. The middle part is the kind of solutions I have been, tools I have been using mostly. And at this moment, my research topic is mostly related to machine learning and cross-chain DLT-based marketplace trust management. If any of you are interested in this kind of topics, I'm open to collaborate. So my presentation today actually will continue with confidential 6G program. Maybe you already heard quite a lot about the background from Veja and Luis from the morning session. So this presentation I'm having today is actually a subtask of the whole project. It's the task 4.1, sorry, and we had a deliverable document from last December, and you can find the document actually on the link I provided here. This document is joint collaboration between different parties. Okay, so I'm starting from here. A little bit introduction to the 6G architecture. So 6G has been discussed for a while, and hopefully it will be coming to the commercial in 2030, hopefully. And for the architecture, here is what has been fantasized. So generally, the 6G architecture for the infrastructure layer will be widely applied on the access of the distributed radio access network, and also the terahertz spectrum, to generally compared with the 5G network, it will have the higher capacity and the lower latency. Meanwhile, this black box here is the network function and the services that the focus in the 6G. And based on this kind of infrastructure, the K architecture change to the 6G will be actually on the network service layer, so which mostly will be transit to the cloud native or microservice architecture. The research around this topic is quite general. It could be the edge cloud or core cloud or public and private cloud. They have different research around them. And in the core network of the 6G, it started to develop the industry verticals to satisfy the different functional and technical requirements. Possibly in the future, let's say the collection of the Internet of Things and time-sensitive network has been very popular. On the top layer with the management and orchestrations, so 6G network will definitely be integrated with the emerging AI and new hardware components. So with all these developments and the components that involved into the 6G, so 6G security and privacy design would definitely require a new regime. That's why I'm here to presenting you the new future for the security and privacy solutions in this kind of architecture. So still going back to confidential 6G, so we all know it's a EU project and focusing on the security and the privacy. But the main research architecture is, as I presented before, that trying to find the privacy solutions using the cryptographic techniques and to supporting the cloud and the edge communication. Three main research pillars. The first, the cryptographic. It's dedicated to find or define the new crypto enabler solutions. Like you may already heard about fully homomorphic encryption, secure multi-party commutation, trusted execution environment, and DLT technology, and so on. So this is very general. We try to adopt all the available crypto solutions. And the second part, the confidential computing, as presented in the various morning session, then trying to keep the data in use and using the trusted execution environment and the containers technology. And the last pillar, the confidential networking, is trying to target the data in different architecture when they transfer from one node to another, and focusing on the post-quantum side and the secure network protocols, data access and general, and using the available, mostly the blockchain technology and federated AI. Of course, in this presentation, my focus is actually on the confidential networking side. I'm going to show you some initial architecture design solutions. We have been really focusing on this confidential networking topic. So first is the basic problem. What's this confidential networking? As you can see here, the cloud, the edge device, and the users. These are like a lot of different entities in the network, and when the different services and the data transmit between them, we have to make sure the data is protected. So, and the use case is in these three applications. The most popular one may be, as we always talking about, federated learning as a services and Internet of Vehicles or secure decentralized data sharing are the main research focuses.
So generalized from these three research focuses, we can actually summarize here, providing you a summary of the main characters of the confidential networking. So first, we need to aims to ensure the secure data exchange and sharing over the cloud or edge, especially. And the second is focus on the orchestration mechanism to improve the data privacy during the federated scenarios. And the last point is data verification and access control mechanism that normally could be leveraged by using the blockchain networks. So before we go into the final architecture design, we first go through the requirement for the confidential networking. So based on the three use cases I just mentioned, we can trying to extract the main requirements for the confidential networking. We extracted the main requirements, maybe around 100 of them from the different parties joined this program, and focusing on the three use cases we just mentioned. And on the right side is an example of the a summary table we used. We provided the requirement and a little bit description, and all the requirement is collected from the 4 categories you see here. We're focusing on functional and non-functional, and also security and regulatory requirements. Yeah, but too easy to understand, later we summarize all these requirements into a general module as we presented here. These 4 modules is the main research problem we come to the confidential networking side. So the first step, the first one is the orchestration part. The first module, the orchestration mechanism, it's about deploying and configuration of the applications, algorithms to different to different parties in a confidential manner. Nowadays, it's maybe more popular using the trusted execution environment or container services. That has been really popular to solve this. And the second, data sharing mechanism. It's mostly focused on the data's confidentiality, integrity, and traceability when the data is shared between the complex networks, 60 networks, and the federated AI. Since the AI is generally a little bit different structure from the existing networking structures, so it actually asks for a separate part to address the problem in the federated AI. And except apart, of course, the federated AI itself already provided some security or privacy for the end users without sharing their data to the cloud. But meanwhile, the poisoning attacks and every attacks that focusing on the federated models is also the threat to the 6G. Last module is about called long-term security. It's basically targeting the quantum-safe communication channels. So, and a good design would really like considering all these modules, like the factors required, and then fulfill this requirement. So to really fulfill these requirements, we of course need to leverage the cryptographic techniques. This including both the software side and the hardware side. Okay, so now I'm going to the fruit part of this presentation is the architecture for this different modules, how we can, the research problem we have been focusing and how we can initially have a design to solve it. So the first one is confidential orchestration. That could be solved the orchestration mechanism required. because generally orchestration involves the deployment of data or algorithms and the executions of the cloud and the edge and different parties. So it's kind of challenging to really cooperate between these different parties, and the container services could be really applied here to orchestrate all this information across different parties. And the initial design here is promoted by VTT, and it provided a solution that's trying to help cloud and the client to communicate with each other in a healthy way, in the privacy way. And on top of the dash line is some confidential, the direct communication between them, and it's definitely not secure enough. So then to implement this security, we have provided two modules here. One is called encrypted container, which is generated implemented based on the existing privacy solutions like a homomorphic or secure multi-party and post-quantum, etc. And another one is trusted containers, which is directly deploy of the trusted execution environment, like which can allow the remote station to cooperate between different clients. Second part is the data sharing mechanism, and as you may already heard that to really achieve the data integrity and the traceability, then the DLT or blockchain technology is come to use. And here with the inherent security and the immutability of the blockchain technology, it can be created for the data sharing between the different platforms across the whole network, thus enhancing the traceability and transparency and everything into the network data. Besides the potential combination between the blockchain and trusted execution environment could also be considered here to providing a better privacy protection generally. And the next one is the federated learning. We have been talking a lot in today's workshop, and you must already know that federated learning now providing a central server to communicate to collect all the parameters from the different clients, and then without the need to really getting the data from them directly. Of course, this solution can providing a very good protection to the clients, but meanwhile, a lot of attacks that focusing on the server side is the concern to the further application of this model. And the research we can see here, we generally provided two. The first is trying to deploy using the blockchain technology actually to providing a poisoning defense strategy for the federated learning scenario. And the second one is actually I think it's from the wind side. Okay, it's using the explainable AI technology to interpret the parameters that are collected from users, and thus when they really detected some sensitive parameters, they will just directly block the user or delete the parameters. Thus, the poisoning defense could be protected. Last but not least, as we see, is the transport layer security. So TLS generally implements the end-to-end security for the data for the users over the internet, and providing the authentication solution for different parties, and allows them to communicate their information in a secure way. And this, of course, will continue in the 6G scenario, and this is almost the most important in the internet network data transaction on the networking side. So to really improve the post-quantum over the TLS is very important work in 6G. And for the long-term security, we have to design the post-quantum solutions for this TLE-based algorithms. And a simple solution would be really to replace the main modules, the key exchange and the digital signature with all the existing quantum-safe algorithms. And I already mentioned hybrid schemes for the future, because the existing post-quantum solution may be skeptical, and then when the quantum-safe solution is not available, then we have still go back to the legacy algorithms. Yeah. So just to summarize here, this whole presentation is mostly to present you an idea of what the confidential networking has been doing and what kind of research aspect we have been targeting, and the initial solutions to all these research problems in the confidential networking side. If you have any questions, because I'm not really an expert on this specific topics, you can I mentioned there the organization name. You can contact directly with the colleagues that I put on the second page, sorry. And yeah, that will be my presentation. Thank you.
Okay, thank you, Shushu. So this brings us to lunchtime. So lunch is going to be provided where the posters are, and please utilize this time to speak to the poster presenters as well. As I mentioned before, ask them questions, try to find out about their research work, and it's going to be beneficial for them, I guess, to pick up some ideas from you as well. So I will see you back here at 2 p.m. for the next and the last 3 technical talks and then panel discussion. So enjoy your lunch, and I will see you back at 2 o'clock. Thanks. Thank you.
Let me check my email first. I don't think so. I just
So this computer only opens photos in Paint. I don't know. Yeah, I probably used it like 20 years ago. But it works. Okay, so your presentation. Rita? Okay, and also sexual technology. Okay, Talita, can you transition to Zoom? Link? Okay, so welcome back everyone. So our next presenter is Engin Zaidan. Engin had been working with us on some projects and yet many projects to come that are, I'm sure, going to be funded fairly soon. And Engin is a senior researcher at CTTC Spain. He brought the good weather to Ireland, so thank you very much for that. When you leave, it's going to be raining again, I'm sure. And yeah, the stage is yours, so welcome back.
Okay, thanks Pat for the introduction. So it's also good to see you in person.
Yes,
we
finally.
were always talking. So yeah, I would like to thank also Matusanka and the NetLab team for the invitation. And it's also my first time in Dublin, so it was a nice opportunity to present and come here. Today, I will talk about this, let's say, this security and trust from a network management and orchestration. So everything will be depending on network management and orchestration. So we will try to build, let's say, topics around this aspect. So, I am working at Services Networks Research Unit at CTTC. Actually, this is the summary of the talk for today. So it will be divided into three. So first, I will let's say try to give some kind of a data engineering aspects for the secure network management orchestration, which is more or less the advanced version of data science. Then somehow try to give some motivation on the blockchain, and especially in terms of this identity management, self-sovereign identity, how we can utilize it in different use cases, scenarios. And then we will try to go finally to this kind of new quantum aspects, PQC, and somehow how we can integrate this quantum key distribution and other kind of developments into the network management aspects. So let's give an overview of the network service management. So yeah, as you may know, this new kind of applications, especially in the 6G, is going to emerge. This holographic type communication, teledriving, this tactile internet, these are all new kind of applications. And somehow, as you can observe, these kind of applications, these distributed computing functionalities in a network environment. So, and also the levels of the service requirements are getting elevated every year, with hundreds of operations at the same time needs to be managed. So traditional way of this kind of service management in kind of human-centric obviously are not feasible, and there should be some optimal solutions that somehow need to be advanced. So for this kind of let's say in the standards, when you go to the network management, this is like a reference architecture proposed by the HC, termed as HC manual. So on the right, you have this management and orchestration functionalities. You have this, let's say, NFV orchestrator, virtual network function managers, and this virtualized infrastructure manager that are, let's say, managing the underlying infrastructure. And you have this VNF manager, which is trying to manage the virtual network functions. So this is more or less the reference architecture. So I think most of the talks will be based on this reference architecture and these derivations that somehow we can utilize in terms of security and trust. So I mean, when you look at like a landscape of the tools, you can also see many open source tools, right? So for example, in the, let's say, service orchestrator domain, you can have this open source Mano, Cloudify, and other kinds of tools. Of course, for the virtual infrastructure manager, you have this OpenStack, Kubernetes. And when you go to the real infrastructure, you can have this open source for Open5GS, Open Air interface, and of course the NFVI of Intel. So this is kind of the landscape. I mean, in terms of the let's say NFV management and orchestration. So what this figure shows is kind of a variation of one of the projects that we were working, which is called 5Growth, which is somehow advanced version of this Etsy Mano stack. So here you can see 2 administrative domains, and each administrative domain is managed by its own Mano stack, which is divided into 3 layers. You have this vertical slicer, which is taking some kind of requirements from the verticals. You have the service orchestrator, which is kind of the brain, and you have this resource orchestrator and service orchestrator, and taking some inputs from the infrastructure, trying to, let's say, link the VNFs together. And you have this resource layer, which is somehow the layer that somehow does these kind of connections on the infrastructure. So here, what we are trying to advance, just the regular Mano stack, is to add this kind of, let's say, machine learning, AI/ML, these blockchain networks, and somehow SSI, or this kind of identity management techniques on top of this kind of Mano layer to somehow add kind of like security and kind of trust. So yeah, when we look at the service orchestration, like secure orchestration, so you could have many choices, right? So first of all, you could have many players in the systems. So, for example, you have these vertical service providers that are providing some services, and somehow you have this infrastructure provider as another player. You can have cloud service providers, multiple cloud service providers, and you can have the mobile operator, which is managing the infrastructure. And on top of it, as you may also guess, we can also add these kind of additional layers with the blockchains, and also you also need to integrate with the regulators and authorities environment. So when we look at this kind of, let's say, regular orchestrators, so there could be many choices where somehow you need to solve this interaction between multiple parties, and somehow also this with the quantum computers coming into effect. You need to somehow organize this communication between these multiple players accordingly. So first I will go with the machine learning part. I think I don't have much time, so I will try to somehow make it like a global picture, because most of the things that are done in machine learning falls into one of the modules here. So actually this is like a data engineering thing, so it is kind of much higher, let's say, vision than the data science with like the regular AI/ML based, let's say, security models. So somehow this is advancing it with the connection modules, data ingestion modules, storage modules, and visualization. And on top of it, somehow you need to manage the data. So this kind of pipeline could be used for this kind of security information and event management systems. And so one example of this, again, is somehow this kind of Mano layer is somehow integrated into, let's say, AI machine learning platform. and with kind of like I would say you could try to use this kind of federated learning, other kind of models to detect intrusions or any kind of attacks with the help of the machine learning model that is somehow embedded into the Mano stack. So the second part is related to the blockchain aspects. So how can we use this in machine management and orchestration? So as I described before, so when you are trying to, let's say, deploy some services, so somehow there could be multiple players here, right? So these services may be deployed by an operator, but operators somehow may need some help from cloud service providers. They can have their own orchestration domains, so these kind of interactions should be secure and also trustable. So in this kind of scenario, blockchain could be helpful. So to establish this trust between, let's say, multiple, this is an example for, let's say, interaction between the multiple players. So if you want to deploy some service as a vertical service provider, you can design a permission blockchain-based network service, and you can have this approval phase from the legal authority or responsible ministry. You can commit, let's say, transactions of the, let's say, management logs, and somehow you can commit it into the blockchain with the help of the regulation authority. So I will not go too much detail, but this is kind of like a stacks that you can build as trust on top of when you are trying to install the network service. So another aspect is this self-sovereign identity. So you can somehow use these kind of techniques as to establish this digital identity. So as you may know, I saw some posters also with the SSI. So you have this kind of an owner of an ID. Somehow the issuer issues this ID to the holder, and holder is somehow showing this ID to the verifier. But in addition to the regular self-sovereign identity model, you can also embed this blockchain. So all these interactions between these kind of entities could be go through the blockchain network. So you can have this kind of, let's say, structure. So issuer can sign the credentials to the blockchain. Holder can countersign it and put it into in the blockchain network. And somehow when holder presents its, let's say, credentials to the verifier can verify it on the blockchain network. So what you can do on top of this is to somehow, let's say, we say that there are multiple stakeholders. So for example, cloud service providers or any other service provider can somehow hold this kind of identity, and they can present this identity to a Mano stack, and Mano stack can interact with the blockchain to verify the ownership of this identity. So what you can see is that somehow you can give these identities, distributed identities to the multiple stakeholders, and somehow you can verify this kind of identity over the blockchain, and somehow also you can automate it with the different blockchain networks. Somehow you can do this identity management system and somehow regular blockchain network to automate it, the process. So what you can do, some kind of use cases of this kind of SSI could be somehow, for example, if you are, I mean, you don't need to do it for the persons or these kind of things. So you can also do it for the, let's say, entities, for example, routers. So for example, in this example, if you are trying to establish autonomous systems, so there is this regular connection. If there is new connection arises, somehow you need to authenticate this, let's say, border router to the system. Otherwise, if it is not authenticated appropriately, it can inject faulty lines and you cannot be able to reach your services. So this could be a big problem. But then somehow, if you can somehow give this kind of identity and its capabilities to the router and import list and router list, and this somehow with the help of this kind of blockchain and SSI, you can somehow establish secure connections. So you can identify the border router that wants to connect to your system. So this comes to the new dimension. Maybe, I mean, this is a little bit different than the regular, let's say, management, control, and data plane. So now we are coming to kind of like an identity plane. You can say something like this. So every time, I mean, as you know, in the zero trust architecture, so you need to somehow authenticate, verify, authenticate all the time. So this comes into the play when somehow these kind of devices, when they are trying to establish connections, you can go to the identity plane and somehow verify yourself to identify your cases every time you interact with another device. So the last aspect is related to this kind of PQC, QKD-enabled networks. I mean, this is already discussed. Post-quantum cryptography is taking effect due to the lack of, let's say, security quality of the public key infrastructure with RSA deferment and elliptic curves. So somehow this is just showing a different aspect. So you can, when you want to design this kind of post-quantum technology in a new network environment, so you need to consider communication aspects, computation aspects, and networking aspects. So you can have different dimensions from device perspective and networking perspective. So from the networking perspective, you can take actions from the, let's say, computation domain, and you can give the requirements to the implementation. And from the device perspective, somehow these protocols needs to be let's say, elevated to, I mean, it's not just TLS, right? So you will have different protocols in the communication. So this kind of protocol advancements should be taken into care and design perspective, and somehow you need to devise this kind of public key system to do implementation. So another aspect in the, when you apply to this kind of orchestration into the post-quantum era could be somehow, let's say, which kind of, let's say, I will say, post-quantum method or computation method should I choose. There could be different computation methods because this kind of encryption protocols are higher order, so you need to have these multiplications in an efficient manner. So it is a kind of a scenario in a vehicular VTX environment. So this is kind of a dynamic environment, and somehow you need to choose, let's say, which computation method you would like to do, because somehow maybe you may want to use multiple cores in the system to do, depending on your load. So these kind of aspects could be helpful when you are trying to do this kind of computation orchestration in the orchestration domain. So I don't know, I will not go to detail, but there is different kind of computation methods like Karatsuba and Tom Cook, and you can try to accelerate your system depending on your choice. So of course, blockchain is also has kind of an attack could be attacked in the post-quantum era. So when we look at a regular blockchain, a private blockchain, let's say, process, so first you have this approval, then you have this transaction phase, and finally you have this block commit phase. So in the regular blockchain, so this approval and transaction phase are relying on these public keys. So this could be the place where there could be attacks, and this is the hashing phase, which is somehow considered to be outside the PQC environment. So here, for example, you can try to, let's say, build your system with the PQC to somehow enhance the blockchain network when you are trying to commit blocks. Yeah, this is just showing an example of how these kind of interactions could be done in a, let's say, network service orchestration. So you can have like automatic guided vehicles, and you can somehow control it with a joystick. And this kind of, let's say, network connections could be established with let's say, monostack. And somehow with the help of, let's say, not only one person could be deploying this service, but there could be cloud services. For example, some of them could provide this cloud environment core network or cloud network, and some of them could be providing radio. So that this kind of trust could be established with these PQC-based blockchain networks also. So finally, this is the kind of a way to proceed when we are trying to integrate this kind of, let's say, QQD networks, let's say blockchain-based identity layers into like a regular application-oriented system. So you can have this kind of like a quantum layer in between where you can exchange the keys. And you can have this control layer on top of it. You can have this management layer, which is regular management, and key management systems, which is interacting, of course, with the QQD layer. And on top of it, you have this identity layer, and of course, interacting with the secure keys. And the applications are using this, let's say, information from the bottom layers to have this secure connection at the top. Yeah, I think this was it so I went over 3 dimensions. Of course, this is, I mean, from our perspective, but there could be many dimensions. So blockchain-enabled management and orchestration, AI enhanced, and this kind of QQD and PQC-based management and orchestration layer. Yeah, this was a brief overview. Thanks a lot.
We have time for questions if there are any. No? Okay. Thank you very much, Angel, again, for this great presentation. So next we have Jürgen Thomas. Jürgen is a PhD student that is working in Friedrich Alexander University in Germany, and his talk is on automated analysis and synthesis of message authentication codes. I'll get your presentation up and running. And, okay, let me share also this. Should work. Okay, the stage is yours. Good luck.
Thank you. Okay, hello everybody, I'm Julian Thomas. It's my first time speaking at a conference. I think everybody of you, or most of you, were in the same position at a conference, looking at all those smart people. Now it's my first time, but I think we'll get along quite well here. We have a talk about automated analysis and synthesis of message authentication codes. That's my personal research field. And for today, oh, that doesn't work. Now it works. And first, I will give a short intuition about what message authentication codes, or short MACs, are. And then I will talk about the relevance of MACs for the 6G project. After that, I will give us short idea, a very high-level idea of our approach and methodology. And in the end, I give a short showcase of our results. But let's start with the intuition for MACs. MACs is a small digital tag which is normally linked to a message, and when you send a message over a network, for example via the internet, you just compute the tag for a message and send it with you. Why should we do it in the first place? Because if we want to ensure goals like the integrity or the authenticity of a message, we need to do it somehow, and message authentication codes are the primitive we use in cryptography. We have a symmetrically cryptographic primitive, which is, in the sense of MACs, the code part to signatures in the asymmetric part, and normally we compute the MACs using a pseudorandom function keyed with the symmetric key. And in practice, we have, for example, CBC MAC, which is not secure in all cases, but the most easy one, I think most of you may know. Then we have HMAC, which is very efficient, and we also have parallel MACs like LightMAC or PMAC. To be a bit more specific, more mathematic, a message authentication code scheme consists of 3 algorithms. We have a key generation algorithm, like most cryptographic schemes. In our work, in our methodology, we don't really care about the key generation. We just assume it is there and it is secure. Then we have a message authentication code scheme, which produces the secure tag. And in the end, we also want to verify whether the tag is secure and everything went well or it did not went well, which is why we have a verification algorithm. The verification algorithm takes the message and the tag and then says yes or no. We also want that our schemes are correct. So if we computer mag, we also want that the verification of our tag and message is correct. We use canonical verification since we just recompute our mags here. And for security, we consider a very strong security definition, the strong existential unforgeability experiment, which when you look in the oracle of the security experiment, we don't only want to have forgeries for messages, but also message and tag pairs. So an adversary may also use an existing tag for different messages, which is just one of the strongest security definitions there are for message identification code schemes. Okay, and our relevance for 6G, let's talk about that. Of course, symmetric key schemes are generally faster than asymmetric ones, which is good for a lot of environments like where you have restricted hardware or IoT devices or mobile devices, which is a very big point in confidential 6G. And we also have good scalability because we can just increase the network without much overhead from our primitive. On the security hand, we have data integrity and authentication. And this can, and for secure communication in our 6G networks, and because we have a symmetric key primitive, we are also mostly resistant to post-quantum attacks. Which is also pretty nice since the standardizations from NIST are mainly very inefficient compared to the existing algorithms. So this is a big plus for our message identification codes. And for the pillars you already saw in the other talks, we are generally considering the cryptographic pillar since I'm at a cryptographic chair. Well, then let's start talking about our methodology. I was studying for the last years now. So our goal is we want to automatically generate message identification code schemes and also analyze their security. And how do we do it? Or why do we do it in the first place? The whole field of message and authentication code schemes is pretty well studied. So our goal was to maybe find new schemes that were not considered yet, but also get a better understanding and find alternatives for the existing ones. And we had a lot of challenges there because for our schemes, when we want to automatically generate them, we also have to consider variable length. So we don't have a fixed environment where we can look at all schemes, but we have infinite many schemes to consider. On the other hand, we want to cover all common schemes because it is a well-studied field. We also want an efficient algorithm to analyze and generate our schemes. Otherwise, we cannot compute our results, and we want as few constraints as possible. So how did we do it? In the first place, we represent mags with direct acyclic graphs. And the nodes in our graphs are simply the computations we want our mag to perform. So here are some of the nodes we consider, for example, a pseudorandom function or the input message blocks and XORMOX. So very basic computational blocks, and we consider most of them. And then when we have our direct acyclic graph and our set of nodes, we can simply just make a permutation over all existing graphs with the constraint of being direct and acyclic, and then we can generate our message authentication code schemes automatically. And it looks like this. So on the left we have, I would say, normal or standard abstraction of a message authentication code scheme. It's the eCVC MAC, and on the right you can see how it would look like within our framework, being a direct acyclic graph. We also have a modular variant for the initialization part, the iteration part, and the finalization, because the most interesting parts are the iteration graphs, because they mainly compute most parts of the message, and we want to look at them. So, this was the part where we generated our schemes, but we also want to prove the security of our schemes. So we created a type system for our graph, and the type system holds the properties we want for our graph, or we want to consider while analyzing our graph. And we have like 4 main property parts. It's type, which assigns the properties to a single node. Then we have dist, which relates 2 nodes in our graph for all nodes in the graph. Then we also need a type for keys, because we have multiple pseudorandom functions and we want to test whether they are independent or not and how they influence each other. And last but not least, we have length, which just stores the length of our messages within the graph. We need the last part because we have nodes like the concatenation, which may increase the sizes of our messages, and so we need to ensure the correctness of our construction. Good, and we use a type interference system to map those properties from our type system upon a graph. And we do it by starting with nodes without any parent nodes, like the import message node block or a counter node block. And then, based on axiomatically defined properties of those 2 nodes, we just start inferring the rest of the graph with the properties we have. We analyzed every possible case that could happen, so our proof should be correct, then our graphs in the end and the properties we did are also correct. And if the last block we have has pseudorandom function properties, then our whole graph we created and analyzed is a secure message authentication code scheme. Okay, and we implemented all of that. It was quite a lot of code, like 3,000 lines of code. And we made it run. And here are some of our results. So on the left you can see how many nodes did we consider for our graph. So what is the size of our graphs, and how many differently keyed pseudorandom functions did we consider. And then you can see how the numbers get bigger with the amount of nodes, and how many graphs we created, secure graphs, are on the left. And on the right we also considered which of those are parallelizable. So those you can see on the right for each column. Exactly, it was quite a lot. Here are 2. On the left you can see CVC MAC again. And on the right we have one graph which is pretty similar to CVC MAC, which has an additional pseudorandom function block. And I just wanted to showcase you that a lot of schemes we found are simply inefficient. So they create new nodes somewhere which don't provide any additional security or any additional properties that are desirable, and just make the whole computation less efficient. But that's not all we have. We also created interesting new ones with, on the one hand, comparable efficiency to existing schemes, but also on the other hand with interesting new properties or properties to consider. And we implemented 2 of those schemes and tried to compare the performance of our schemes with existing ones, and we see that they in some cases are, or not in some cases, but in general are comparable to the existing ones. So we have found alternative schemes, but on the other side here are parallel schemes may also be slightly more efficient than existing ones, because especially regarding parallelability in computation, it really depends on the setup you are using and the hardware, where one can be faster and the other can be less fast. Okay. Thank you for your attention.
Okay, so do we have any hands up?
I have a question.
Yeah, of course.
So does MAC provides the non-repudiation?
Sorry, I didn't quite understand that.
Does this message authentication code provides the non-repudiation? Non-repudiation means okay.
I don't understand the term. I'm sorry.
Just say that again.
A non-repudiation. It's a security property to ensure that yes, X has sent the message. Suppose the communication is between X and Y, so they are using the MAC. So using the MAC, like Y can be assured that this message is sent by the X.
So you can say, okay, this person sent a MAC like in a signature scheme where you have the public key and say, okay, he really signed his message. If you have a secret key exchange with this person of, I think it should be possible, because only this person you have made your secret key exchange can create those. But if someone is doing a replay attack, you don't know from whom you may not know from whom the message is coming.
That's what I'm asking.
Okay. Yeah.
Yeah. So if you sort of randomly build all these different potential MACs, and then you check for whether they match the actual properties that you want, right?
Mm-hmm.
And what was the desired property again? Like it acts like a PRF.
So the whole scheme should fulfill pseudo-randomness, or should be a pseudo-random function, in order to be secure in general.
So how do you check that?
Yeah, by checking the property of every node, and it's a direct acyclic graph, so you know this is the last node in the whole graph, and there won't be any further nodes. And if the function property of this node is pseudo-randomness, then you know every time you compute the whole graph and land at this node, you have this property.
Okay, yeah.
Perfect.
Okay. So, well done on your presentation. I think it was excellent.
Thank you very much.
Okay, so now we have Madhusanka that had been already introduced to everybody, and his talk is on blockchain-based consensus mechanism for detecting spectrum access variations. And I will let me share the screen and make it full screen. Okay, I will hide this. Yep.
Okay, good evening everyone. So I'm going to present our research work related to the, one of the research work related to the confidential 6G. So where we are developing a new consensus mechanism which can be used in order to collect the spectrum information. So we call it as a proof of sense, so because it was developed based on the spectrum sensing. So it's a new blockchain-based consensus mechanism, so we can be used in order to detect the spectrum usage. Later it can be used to enable the dynamic spectrum allocation, and also to detect any kind of spectrum violation which can be happen in the mobile network. So we talk about the spectrum sharing. So we know the wireless radio spectrum is a natural resources, and it is really expensive. And we have to manage it properly if you want to enable future networking services, for example, 6G or 5G or even 6G scenarios. So we need to manage this spectrum properly so we can provide the services for more and more mobile users. But for the moment, the spectrum is managed centrally, so every country has a regulator body who's managing the spectrum and deciding who will be using the spectrum. And also we know the spectrum is very expensive. For example, the 5G spectrum, the new radio introduced just for 5G, was almost 6.5 billion cost in Germany. So it's a very expensive natural resource and we need to properly manage. But unfortunately, if you look at the spectrum usage for the current scenario, so most of the time the spectrum is underutilized. So most of the time it's only 6% is occupancy happen in the spectrum. So even though it's very expensive, it's not properly managed, so the people can fully utilize the spectrum for their usage. So one of the main reasons like we are having this kind of white spaces or underutilization spectrum is the centralized management or the fixed spectrum assignment policy, which is used all around the world. So in order to solve this problem, actually we have to go for this dynamic spectrum allocation scenario. So instead of going for fixed spectrum allocation, we have to go for the dynamic spectrum allocation. In that way, we can share the spectrum more efficiently between the different users. So always the dynamic lease is better than the static lease, because whenever a primary user or whoever owns the spectrum is not going to use, he can lease it for another user to use and use for their communication. And the dynamic spectrum allocation was studied for over the last 20-30 years, and it was well studied area. There are many different dynamic spectrum allocation mechanism has been proposed. For example, this pro-primary spectrum sharing, that means multiple owners can own the same spectrum, so they can share according to their agreement. Or cognitive radio is also another scenario. It's very interesting. That means there's a primary owner for the spectrum. Whenever he's not using the spectrum, he can rent it for the secondary user. And the spectrum access system is defined for certain restricted frequency band. And also the local private mobile network concept has been developed in order to provide the spectrum usage for a certain area. So there are different dynamic spectrum allocation mechanism has been proposed, but unfortunately they are still not used anywhere in the world due to several issues. One of the biggest issues is the untrusted stakeholders. So whenever primary owner wants to rent the spectrum, they have to trust the secondary user. And also we have to make sure the secondary users will not overutilize the agreement or agreed the spectrum, and we want to detect these kind of spectrum violations. But for the moment, there is no real-time spectrum misuse detection systems available in the world. So one of the main reasons why we don't have the real-time spectrum violation detection is there's no way we can collect the real-time spectrum sensing information in the reliable manner. So what we do is in the present day, if you want to detect any spectrum violation, regulator has to go manually a certain area and send the spectrum and to identify who's transmitting on which frequency band. So that is time consuming and manual process, and it can't cover the whole spectrum and also the whole region of a country. And the second problem is like if you go for a third-party spectrum detection mechanism, or for example, if you ask the mobile operator to do the spectrum sensing, then we have the problem of the bad data issue. That means spectrum, maybe the mobile operators or even the third-party spectrum sensors can upload the unreliable data. And because we are talking about like penalties of 100,000 or 200,000 euros penalties, so the data has to be verified and trusted. So that's also another issue we are facing, because we don't have the reliable spectrum sensing data available in the current system. So how we can solve this problem? Actually, in order to solve this problem, there are several solutions have been proposed. So one of the solutions is proposed is the blockchain as a viable option for dynamic spectrum allocation. Especially blockchain can be used in order to enable a certain kind of marketplaces, so where the primary users can sell the spectrum for the secondary users. So there are many benefits we can achieve with the blockchain system. But if you just use the existing blockchain platform for the dynamic spectrum sharing or the scenarios, there are different challenges we need to address. So one of the biggest challenge is the expensive blockchain operation. So normal blockchain operation is expensive, the consensus algorithm is expensive. Most of the time the consensus algorithm used in the blockchain system is not designed for this particular task, it's doing something more cryptographic heavy mechanism. And also still none of the blockchain based systems are able to collect the spectrum sensing information, reliable spectrum sensing information for the misuse detection. So in order to address these two problems, actually we have proposed a new customized blockchain consensus algorithm which is specifically used for the dynamic spectrum access. So we can design a blockchain which is energy efficient and also low cost, and also it is able to collect the reliable spectrum sensing information across the region or even in a country. So let's look at how our consensus mechanism is working. So we call it as a proof of sense, so because it's based on the sensing operation. So what we do is like we will be using different spectrum sensors, so third-party spectrum sensors across the network or anywhere in the mobile network. So they will be capable in order to sense the spectrum. So basically listen to the network and capture the information transmitted through the radio spectrum. So the first, in addition to that, these nodes will be generate a key. Actually, they will generate one key and it will be divided into certain part, and they will sign it, and it distributed between the different sensors in the network. And each of these sensors will be transmitting this key part randomly across the network. And all the other sensors will be capturing the key part transmitted by each of these sensors in the network. So the nodes will be listening to the spectrum in order to capture this randomly transmitted key part. So by the time when they are trying to capture the key part, they also collecting all the spectrum information which is happening during this listening period. So by listening to the network, they can capture different key parts. Whenever a node captures enough key parts, he can become the winning miner to create the complete key. For example, let's say there are like 5 parts of the key. Whoever collects the 5 parts of the key first will become the winning node who can create the key, and he will become the winning miner, and he can create the next block for the blockchain network. So at the same time, when you are creating the new block, he will be uploading all the sensor information, for example, spectrum sensing information, to off-chain blockchain, off-chain storage, and that hash of that off-chain data entry will be also added to the new block. So in that way, he will be including the captured key part, the key, and also the spectrum data which he has been collected during the listening period. So the other nodes can easily verify whatever the key has been included in the new block is valid or not based on the key part owned by each node. So if it is a valid node, everybody in the blockchain will be added the new block into their blockchain. So in this way, so we can create a new consensus mechanism just listening to the spectrum. We don't need to do any high-level cryptographic mechanism to decide who is the winning miner. So this is the block structure actually we have proposed. So basically in the blockchain, if you look at the block, we have 2 different parts, header information and data part. So the header information is typical blockchain information is there. we have added two new data types. So one is the spectrum data information, like the winning key and those things will be added here. And also the sense data will be also added as one of the block parameters. In this way, we can share the spectrum, the sensor spectrum data with the blockchain. And also we need to have a mechanism to motivate the people to participate this kind of mechanism. So we have thought about like 5 different ways we can run the blockchain network. So the first way, like we can get money from the subscription fee. That means whoever the users who want to use the data, they have to pay a subscription fee in order to use this spectrum information. So this spectrum information is important for different people, like for example, ORAN customers who want to optimize their network, they can use this spectrum information, or regulators who want to do some kind of analysis or even enable the dynamic spectrum access, they can use the network, so they have to pay a subscription fee in order to access the data. And we are proposing a transmission rewards. That means we have to encourage all the nodes to transmit the key part. So in order to work the system, so the miners who are transmitting the keys will get in the transmission reward. So the block generation reward is there. It's normal block reward. So whoever creates a new block will be getting the block generation reward. And then we are introducing 2 other things which can be used based on the data. One is the fraud detection reward. That means if the spectrum data which is collected by one of the miners has been used for a fraud detection, for like misuse detection, he will be getting some percentage of money for their contribution. And also we know the spectrum violation will be fined. So if you detect any kind of spectrum violation, so the percentage of fine will be also going to the system, so we can operate the blockchain system in this way. And we have also did some experiment to see how this system is working. So especially we have created the spectrum sensors using HackRF device. So this is the software-defined radio mechanism. It can be transmit and receive the radio signal, and we have coupled it with the Raspberry Pi, so we can do the processing part of the blockchain. And these are some kind of experiment results. So here you can see the execution time and the energy of the consensus mechanism. So you can see the consensus mechanism has the comparable energy usage as proof of stake, which is used in Ethereum, and it has a lot of better energy usage than the proof of work like blockchain kind of scenario. And also the execution time is also quite comparable compared to the other scenarios. It's a bit higher than the proof of stake, but it still is like 15 seconds. It's fine when you consider about the Ethereum kind of network. It still have like 15-second block time. And also we take what is the end-to-end delay of the proposed system. So we can see it's around 15-second time range for the whole system. And also one of the most important thing is like when you consider a consensus mechanism, how we can change the difficulty, like how we can change the block time. So there are many parameters we can be used in order to change the block time. So the key, what is the length of the key, how many shares we are going to use, what is the threshold, that means like how many key parts need to be captured, can be used as like one of the features to change the difficulty of the consensus mechanism. But we are not rely only on the cryptographic part, but we are rely on the wireless channel part mostly. So there are different parameters in the wireless channel, and also the different parameter related to the transmitter and receiver can be also used to change the difficulty of the consensus mechanism. So in that way, actually we can say our mechanism even quantum resistant as well. For example, if there's a quantum computing, it can be break only the cryptographic part. Still the wireless randomness cannot be break with the quantum computer. So we have our system even have the quantum resistance features as well. And here's some more experiment just to show like how the key recovery probability will be changed with the different parameters, with different noise channels and different encryption mechanisms, and how encoding mechanism, how it will be impact on the system. And also we check the noise end-to-end delay, how will be impact with the noise level. And you can see the wireless channel characteristic has a huge impact on the key recovery time. So that means we can use the wireless characteristic to improve the difficulty of the consensus mechanism. So we have several publications. Actually, Pramita is here. He is the main guy who was doing this work. So we have 2 transaction papers with the different 2 versions of the same proposal. And also now we are working on the demo, full demo of this setup. So we are hoping to present it in 1 week time in ICBC in Dublin. So, and also we were like also looking at like different blockchain system, not only the blockchain system but also other distributed ledger system, for example holochain as alternative, how we can adapt the holochain to implement the same system. So we have some preliminary results already published, but still there are a lot of work we need to do there. And the future works actually we will be focusing on, for the moment we have the concept of developing the consensus mechanism, but the usage of the data hasn't been studied yet. So one of the future work we will be working on, like how we can design a marketplace so we can share this data between the different stakeholders, and also using AI-based smart contracts to automatically detect the violations. Especially we can automate the violation detection part and also enable the dynamic spectrum access management. And also we will be working on how the spectrum can be shared with a non-fungible token. Actually this work has been already done by Lavan, one of my PhD students. So we have preliminary result that will be also integrated with that. And another area we want to see like how we can detect the bad RAN data problem, because even these sensors can upload bad RAN data. So we need to have a mechanism to detect this kind of bad RAN data problem. So yeah, I think that's it from my side. If you have any question, I'm happy to answer. Yeah.
You mentioned it's very expensive actually for to use blockchain technology. Is there any hope in the future to reduce the cost? Do you see the cost diminishing?
Sorry, I didn't get.
You mentioned it's very expensive.
Mm-hmm.
That's one of the issues with using blockchain. Do you predict in the future it will decrease?
Yeah, so that's what actually one of the our work we have done here. So for example, we have reduced the cost of energy usage. So the proof of work is the one mostly used in the scenarios like, for example, Bitcoin is working on the proof of work. And the proof of stake is something more energy efficient like Ethereum is using. So our scenario has like comparable result. It's quite energy efficient compared to the proof of work kind of scenario. And in our system, we are not focusing on computational heavy calculations. That's mainly the cause for high energy and high cost of operation. So this kind of approaches will be reduce the cost of operation of the blockchain actually. Yeah.
I was curious with regard to the people sampling the spectrum. So for instance, IoT devices, phones, other things like that. So is there any indication from any of the providers of wanting to participate, or how you would go about embedding the hardware there? Because I think in some of the presentations outside the posters, there was specialist hardware doing sensor stuff. So embedding that hardware directly in the phones or the IoT devices is part of their underlying capabilities in order to self-report? Is there?
Yeah, actually we don't need special hardware. So actually this research work. So we were like trying to do use your mobile phone. Actually, if you have an app, you can do the same thing. So I mean the spectrum monitoring can be already done with the mobile phone because it's capable to scan the network and capture what is happening in the network. So we just need the app installed in the mobile phone to get that data.
And then if a phone, somebody syndicating phones or hardware was the person initially providing the bandwidth, then maybe they would like to own the market to resell the value of their customer who is operating the phone or reporting it across their network back to you. So is there some framework there for thinking about how the network operators would participate as buyers and sellers within that blockchain framework of value exchange?
Yeah, actually that's like one of the things we were thinking, like to operation here, like the subscription fee based system. So if somebody wants to use this system, so they have to pay something. For example, if the mobile operators are willing to do maybe little bit extra, like integrating these devices, maybe we have to give like a discounted fee for or something, or maybe access to the data for lesser fee or something. That kind of approach we have to consider. But we haven't done this market analysis part. That's still open question to do, and how we can get money out of it. So that's the important part to have.
And just a quick follow-up question. With regard to the activity data for the current usage of 5G networks, so each network, they report possibly on the individual coverage of phones, and maybe they self-report back to the base station, and each of the base stations can monitor the amount of ingoing network traffic. But is there much of a high-quality communication between network providers at the moment? Do they have like an exchange mechanism for reliable, verified reporting between themselves of how the infrastructure is being utilized, or is it sort of haphazard in how they report to each other and the regulator?
So usually beyond the base station, most of the time we have this optical communication, right? So I mean they are not relying on the wireless communication anymore. So I think that kind of setup can be used in order to exchange information between them. So we don't need the wireless part beyond that actually. Yeah. Any other question? Okay, thank you very much. So we will.
We're 30 minutes ahead of time this time, which means that we have two options. We could either take the coffee break and then do the panel, or do the panel and then do the coffee break. Manisanka, which way do you want to do it? Do you want to do the panel and then to kind of wrap up with the coffee? Or
what time is now?
It's exactly 3 p.m. So we have it scheduled for 3:30.
Oh, maybe we can have the panel now. It's okay.
And then this way we can just wrap up quicker, and then whoever wants to have coffee will have coffee. Josh,
you want to have a coffee now?
Yeah, I would prefer that we have a coffee break and then a panel.
Okay.
Okay, so let's just have it now. I mean, it's gonna. So let's maybe say like 15 minutes.
15 minutes.
But I'm not sure the coffee will be ready.
That is it. Yeah, we may not have the coffee. that will cancel your mysterious plan, Rashko.
Yeah, I think that. But we'll find out.
Okay, great. We'll just begin with this panel session. So again, I'd like to welcome all of you once more to the stage. And Drashko, the stage is yours. You can use as much time as you want. The coffee is at 1:30, however. I'm just saying.
Fantastic. Thanks a lot. Thanks to all the panelists. So this session, this panel discussion is called "Exploring Security and Privacy in the 6G Era." So just to give a little bit of context, you have a short abstract that I can read, and basically, I'll read it literally. So, as the world eagerly anticipates the advent of 6G technology, ensuring robust security and safeguarding privacy stands as a paramount concerns. The idea is really to, in this discussion, address several questions related, of course, to the security, but with maybe accent also on the privacy preservation and also on the, let's say, parts of the system, of the telecom system or network systems, like, for example, touch also on the modest devices, on IoT, edge devices and sensors, in which security is also a challenge. So I maybe just to give a context, start with a, let's say, very general question. So having in mind the 6G architecture that is in development and that maybe we don't know yet how it will look like, but what we know for sure that the services and service orchestration will be much fine-grained and much more developed. And having in mind the advance in artificial intelligence as well and its usage in 6G networks. So I would like to start with the question maybe to all of the panelists is, what do you see as the biggest challenge or the let's say the set of challenges that will be especially important to take a look at in the future 6G networks? So maybe Luis, I want to start. Maybe go through this.
Okay, I think that perhaps the main challenge that we have ahead of us that with these 6G networks and IoT environments, we have highly dynamic environments and very low protection for some of these devices. So trustworthiness on the information we're gathering from these devices is one of the main challenges for us, especially for someone like me working on AI, because that opens the possibility of many things that can go wrong, like the poisoning attacks that I mentioned before. More on the system side, I think that this leads to problems related to the interconnections between the threats that we can see. So this cyber physical system security plays an important role in this area. So looking at the intersection between hardware security, software security, and the applications that we're running on top of that, like AI systems that we can build on this architecture. So we have a lot of challenges ahead of us, and the interconnection and understanding the intersection between all these components, I think, is paramount.
So the heterogeneous nature of the
exactly.
Yeah. Thanks. Engin, what is your take on this question?
Yeah, I also agree with Luis. The complexity of the system is getting much bigger and bigger. As we progress with 6G and this kind of new technologies are emerging, and we want to integrate them into the system. So these kind of technologies are also emerging from the IT cloud domain, and somehow we are trying to take them to the new technologies. So when you have this kind of functionalities that somehow also you want to make it distributed, first you have to manage the underlying infrastructure, because somehow the things that you need to provide should be, let's say, SLA guaranteed, and these kind of things are important. And somehow, I mean, when you raise the kind of surface, you also make it vulnerable to attacks. This kind of quantum things are also emerging. So somehow, I think the biggest challenge that we are going to face with the infrastructure will be the complexity that will come with the new kind of threats, and how we can manage this kind of infrastructure.
Thanks. Christina, do you have maybe something to
add?
Or
they're covered. It's just my views are from Engin and Luis. What I would like to add on top of that is like, yes, new sensors, new devices are to be incorporated in 6G. So there are technologies that we're not aware of already. Yeah. Yes. And also data that are to be shared that we're not, maybe even more sensitive. So yes, we are asked to do something before knowing what it is to be ahead of. Or maybe data will be stored right now that cannot be decrypted, but they could be decrypted in the future. So maybe we need, in 6G, we need to protect better the data that are exposed for future abilities in in cryptography. So
thanks.
Yeah.
Thanks. Nenad, your take.
Yes. So I'm more of the edge guy. So from the edge side. All in all, I think it's well covered from the colleagues. From what they said, I fully agree with that. I can only add that we are even now not ready for what we have now, for 5G and 4G even. I mean, data that are sitting in some clouds that are going to maybe eventually become opened, as you said, at some point maybe decrypted. But even now, if you do the screening of many systems, you will have a lot of severe data leaks and a lot of issues. So I think this is a big topic that we need to pay attention and to watch and follow these groups that work on standardization that can help us understand basically what are the pain points. You see there's a lot of algorithms proposed that are being broken after several of weeks by NIST. So at the moment, I think if you look from the infrastructure side, there's a problem. On the edge side, there's a problem. For the data in transit is a problem. Not speaking 6G, or speaking now.
Yes.
So, yeah.
Understood. Okay, Shushu, what is your take on this? A lot of has been covered, but...
I got it. I think the multi-platform and the industry requirement from different like drones, robotics or IoT, this are already asking a lot of a change in the 6G, and it's kind of challenging to do it. But on another side, which related to our workshop today, I think like the crypto, in the basic level, like a crypto solutions, that is not enough to really provide a smooth transition of data from platform to platform yet. And that would be a really adventure that we need to achieved before we can really move into the 6G security scenario somehow.
So speaking of this, so the cryptographic or the cryptographic protocols that we have today are in danger, we can say, because of the quantum computing, the Shor's algorithm, and the possibility of those to be broken, which we don't know when, but it might happen. Typically, some of the data might be, let's say, important to save for 50 years, maybe some military or governmental data. They can be recorded and then reversed, cracked by brute force quantum computing. So maybe the next question would be, how do you see, let's say, emerging of post-quantum cryptography or quantum-safe cryptography within telecom networks? Do you see it happening now, today, and working on this? So maybe I'll start with Christina, who mentioned this previously.
Yeah. So the question is how do we attack this? Or,
yes.
Yeah. Currently there are some like fully homomorphic encryption that we mentioned during the presentations. Well, let me go one step before. So some mathematical problems are expected to withhold quantum computing. And one of those mathematical problems is lattice-based calculation. So, and now moving forward, fully homomorphic encryption is often based on lattice-based computations. So one option is to really look into fully homomorphic encryption, as it is something that we have now. And we hope, but based on not hope, it is based on facts, that it could probably withhold that. So first is fully homomorphic encryption, and then yes, to look into other mathematical problems that are expected to withhold that. This is the first that we can do now.
That we can do.
Yeah. So this is.
Recently, there was, let's say, a little bit of earthquake in the cryptographic community because of the lattice cryptography was almost, let's say, proven inefficient or broken. I think it was learning with errors type of algorithms. Maybe question for Nenad, you know, how do you see, you know, do you see also emerging of those new tools and their application in the industry today, and their how should I say usage, practical usage in the telecom industry, and then in other industries that rely on telecom?
Yeah. So as mentioned, from I can speak from the edge side more.
Yes.
So it's not strange that big companies are acquiring a lot of hardware resources. So GPUs and HPC will be the next big thing.
Mm-hmm.
I'm just not fully, I cannot grasp how it will scale to the point that you can implement something on the edge side that can have that much performance and not kill the device. So I think some breakthrough in the cryptography should be done to be able to cover everything, and some balance and derivation should be imposed to be able to develop the algorithms that can at some point be bulletproof to post-quantum at the same time, and to preserve some, let's say, efficiency. So I cannot answer directly what you said, because it's very, I think it's a broad topic in the research nowadays, but I think everything will revolve how much resources you will have at some point, and how much you can decrypt or encrypt with your resources. From the telco side, it means that you need to go end-to-end, which is very demanding, because you need to have a car is not a problem to have this, but if you have the IoT device, it's a hell of a problem, because the constrained device cannot support what you need to impose. So I think it will next decade will show and will reveal what we all will have to witness in these years. How will next 50, 100 years will look like? So it will probably be for everybody of us something completely new from the standpoint of what we use in-house. I mean, when I say in-house, we really mean in our house. So you're going to have a camera in your house, a phone in your house, or is it going to be, you know, completely going off of the grid because you are afraid of everything? Everything can be monitoring or seen. I mean, I'm not going now into too much discussion, but you all seen what happened with Facebook and Snowden and all this kind of stuff.
Thanks. So maybe, Engin, to stay a little bit on this post-quantum cryptographic questions, do you see it applied in the blockchains and these kind of scenarios or more on the, let's say, cloud network protection, or in the architecture of the new networks, where do you see them fit?
Yeah, I think post-quantum is kind of like going to be necessary. I mean, it's not like, okay, I mean, it's not like something IP version 6, okay, we can delay it. So at some point, we should use it. So I think that will increase the adaptability to be able to use this kind of algorithms, because at some point, if it hits some border, people will try to test. For example, when we see kind of like where it is used currently, we see that it's mostly focused on TLS, right? People try to access website, and I see like many experiments that somehow maybe it's failing at some point. It doesn't get client hello message. You need to send it twice. This kind of breaking. It's not adapted to the previous versions. So there are these kind of tests, especially for specific protocols. But I think at some point, I mean, if it is advancing technology advancing like this, at some point we need to somehow extend it to other protocols. I mean, especially IoT and other kind of, I mean, even in blockchain. I mean, there are vulnerabilities that somehow we are using this kind of private public key infrastructure, and these kind of things should emerge. I think it will emerge eventually. It's inevitable.
Shushu, maybe a question also. I would like to hear your opinion on this, but also to continue maybe with the on the architecture side. For example, what we are seeing with 6G, as I mentioned, the service orchestration that is more kind of elaborate, more fine-grained, relying also a lot on the function as a service. For example, we are seeing the workloads being smaller, or the usage of, let's say, WebAssembly, or as a kind of also way to safeguard the binaries and limit them. So maybe also a question about that kind of architecture. How do you see those security challenges, having in mind micro VMs, all this new way of containers, let's say, that are then orchestrated in some way, maybe not through Kubernetes, maybe through something else?
Oh yeah, I can first answer the post-quantum.
Yes.
Yeah, so for the post-quantum, I think I maybe read something about the post-quantum, quantum safe blockchain is somehow already deployed already. And another thing, like on the 6G infrastructure level, I would say, like as I presented today, the transport layer TLS is really important, because it's a basic protocol that to secure the communication between like end to end, and it's actually very easy to enhance them with replacing the existing algorithm with post-quantum algorithms. And so on the network side, I would say this is a very important first step, and already provide a huge quantum safe to the infrastructure on the 6G generally. Yeah. And for the second one, the security from the container side, yes. Well, from the secure, like now Intel has many services that already, the product already come out that having quite a good performance, but the execution protection is still very limited with the operation that's allowed inside, and the complexity of the dealing with the network data, which really is like a huge amount. That would be really challenging to deploy this container into the existing age. I don't know exactly, because the complexity of the remote attestation that allows you to verify your identity and everything is quite heavy, and especially in the Internet of Vehicles, when the car are always moving at a high speed, it could be really challenging in this kind of scenario. Yeah, but still like lots of work to do in the future.
The communication overhead and plus attestation.
Yes, especially when the moving speed is quite high and then the latency would, I don't know if it will actually hold. Now most of the experiment is tested with like static environment and it's not really on the moving side yet.
Okay. Luis, I know you worked a lot on the federated kind of, distributed systems. So I would like to ask you also your opinion on this, I would say, more fine-grained kind of orchestration and breaking those, let's say, or using other kind of containerization, not only, let's say, Docker containers, but other types, as I mentioned, maybe WebAssembly, maybe some other way to move those services, micro, nano services through through some orchestration fabric. Certainly that will open new security challenges, and so what do you think about this?
Well, on this area, I have worked less, but one of the challenges that we have when we try to apply containers to machine learning models is that the complexity of the machine learning models somewhat limits this execution on a trusted execution environment. So you really need to segment a machine learning model across different containers, for example, to make some of the solutions viable. It's some of the things that I've seen so far. On the distributed learning side or the federated learning side, depending on the application, but I don't have much concern about how to run this on container, but on how to orchestrate this on a very high dynamic environment with patterns of change on the connectivity that happen very fast. How do you deal that from the algorithmic perspective? How do you orchestrate that, for instance, using hierarchical aggregation? And how do you handle hundreds of thousands of users providing data that comes from untrusted data sources? So orchestrating that learning process across so many participants, that is the main challenge to me when coming to the federated learning part.
Mm. And in similar question, what is your take on maybe these kind of policies or other security, technical approaches to the service management in general within, let's say, underquote 6G architectures or new network architecture?
Yeah, I see kind of like a trend was in 5G was more like a centralized management. You can have this kind of like a system that tries to do, say, more or less centralized, and with the kind of these new services emerging, so now you need to move kind of a distributed management systems, and somehow maybe you need to have this local, let's say, managers at every places, and at some point, it also brings some challenges, of course. Somehow they need to synchronize because the services should be end-to-end. And somehow the decisions, there could also be conflicts in decisions. The local decisions done by the one system could deteriorate the overall service because they could not be aware of what they have done to the other places. So these kind of conflicts, these kind of synchronizations, things, they are not there in centralized management. So if you move towards this kind of like distributed management, you will have different challenges, and somehow this brings new things in addition to the benefits. So this is the things about it.
So we mentioned, several times the importance of the privacy preservation within 6G networks, but this is something that we have today. So the privacy is a very important issue, not only because of of course, the end user privacy, but it becomes even more important in the context where artificial intelligence needs a lot of data to be trained, and data can actually come from different from different sources. We've seen, the extremely huge amount of resources that are needed to train new GPT models, and also the problems that arise from the IP, from the intellectual property of the data that was used to train those kind of models. So in order to have higher quality models, we need a lot of data, and because now the data needs to be taken from other companies, organizations, and they need to protect this data, and they need to, often this is also regulated data, and I wanted to, that we discuss maybe a little bit those privacy and preservation techniques or enhancement technologies. So Christina, you mentioned the fully homomorphic encryption as one example of those. So what is the current state, let's say, of the ecosystem, or what is the usability of the technology today, and what needs maybe to be done in the future so that it becomes more approachable to engineers, and so that they can finally start building systems using this kind of technology?
Well, I believe for sure there is more research to be done from the mathematical aspect, but also, like you mentioned in the presentation, we need to also enhance with hardware to have higher computational power dedicated only for that, like GPUs or machines dedicated only on computational cost. Though, on the other hand, to just to make the devil's advocate on my argument, then, like I said, we ask for more from the end users, which again, it's something that we need to think of. But maybe in the end, it's something that we cannot avoid. And actually, well, the technology grows exponentially.
Maybe this trade-off will make sense, and maybe they will accept using ASICs or some other accelerators in some cases, as GPU started for this. We needed them to accelerate graphics, and now NVIDIA is the richest company in the world.
Exactly.
But if I may say something, I think that here we should, by looking from the perspective of an AI model, we should differentiate between confidentiality and privacy. For instance, the fact that you apply fully homomorphic encryption protects the confidentiality of the model, so you don't have access to the parameters of the model. But that doesn't mean that when the model is deployed and you query the model, you cannot infer properties from the data used for training the model. So that doesn't enforce the privacy protection of the data used to train the models. So the set of techniques that you perhaps need to apply are different. And this is a problem that I think is going to be important now with the growth of large language models, because obviously for many companies and machine learning practitioners, training a large language model from scratch is infeasible. It costs millions and millions of euros, dollars, or whatever. Yeah. So basically, we borrow one model and we fine-tune the model. So if we don't have much data to fine-tune the model, we are prone to overfitting. In other words, we may memorize we may make the model to memorize the data that we use in this fine-tuning process. So the use of privacy-preserving techniques like differential privacy can be a good option to try to mitigate some of these problems. And it's also something that we see on federated learning. So we advocate that federated learning is a privacy-preserving technology, but we need to put some other tools on top of that to prevent some of these problems from happening related to the memorization of these large language models. And I think that this is going to become an important problem as we start developing more and more these language models. So now we start to see solutions based on generation of synthetic data. That's going to be an important topic in the next few years, especially because we're going to face a problem of data scarcity for training these models, because so far these models have been trained scraping data from the internet, but some of these, let's say, data providers are closing their APIs, so the access to that data starts to be more difficult. So we're going to resort more and more into this synthetic data generation, and there can be also challenges associated to privacy when using this synthetic data generation method. So let's see what happens.
What kind of privacy can be breached if you are using actually something that you synthetically generated?
Because again, maybe the methods that you use can memorize some of the properties of the data that you use to train that synthetic data generator. So it can reveal some properties of the data that you have. Apart from that, it can create other series of problems, for instance, related to diversity and representation, so problems related to fairness on artificial intelligence, or how to represent better underrepresented groups.
Yes.
Yeah.
Yes, really
It's not related to privacy, but
yeah. Very good point. I mean, so we are somehow trying to solve the problem of confidentiality through either through cryptography, fully homomorphic encryption, or acceleration of this cryptography through trusted execution environments. So we use the CPU extensions to encrypt the RAM, but the overall idea is to protect the execution, to protect to protect data in use, right? But that doesn't actually prevent anybody from doesn't prevent algorithm from stealing data, even though this algorithm is executing in a black box.
Revealing data.
Or revealing data through the model weights or something like that.
Because you query the model, you don't have access to the parameters of the model, but by querying the model, you can get information from the output of the model about data that could be used for training.
I actually have one point to add here. It's kind of reminds me the research I've been working on is called machine learning. So apart from like using really differential privacy to protect users' information before feeding the model, another research topic close to this is like when we use the service, we agree to them to use our data, but once I get out, I stop using the services, I hope the model could stop recording my information and also remove all the data I have been contributing, which is the idea of machine learning generally. And I think that's also a very interesting direction for the machine learning to go in the future.
Yes, but I mean, there has been work maybe on the explanatory AI, or maybe that we can find out how the algorithms, how did we come up with this model, and can we understand, why it looks like, is it malicious, right? That's really, I think, still unsolved problem.
I think so, and to me there's a caveat on the use of explainable AI. So because we tend to use it as an oracle. So okay, I have explainability, so I know that the algorithm is doing right. Okay, can we trust that explainable component of the AI algorithm, because it may suffer from the same vulnerabilities, of the same weaknesses as the main algorithm. So how can we trust the explainability method? So it's not an answer. Of course, it can help to provide some insights on the reasoning of a machine learning model, but at the end of the day, it's as brittle as the machine learning model itself. For instance, in the presence of an attacker can easily deceive both the main algorithm and the module doing the explainability. So still, I think that we need more in order to enforce the trustworthiness of the machine learning models.
Yeah. So, Stina, you mentioned that you use both federated learning and fully homomorphic encryption in your presentation. So actually, I think this what we discussed here actually prompts the idea that we need to use the combination actually of multiple privacy enhancing techniques in order to achieve this protection of data actually.
Yes, yes. Well, we have not combined it yet. We are to move forward right now with what we have, and yes, again, we need to see the trade-off, and in case study the cases where it is useful, where the data are that sensitive, or the model is that simple to use, because as the computation start to get more complicated, then it's not just adding and multiplying. Maybe you need to have more involved computations that add a lot of computational overhead. So yes, it's a combination of techniques, tools, software, hardware, and as it was mentioned in the second talk today, we're studying it. We will never know. We just try and miss and success. So yes, I think this is the approach for now.
Yes. So Nenad, you also have been using federated learning extensively. So what is the current, let's say, software or hardware ecosystem to make this reality and for this to be really useful? It's related to the also capabilities for the calculation on the edge. This way of training becomes more and more, usable.
So I would say healthcare, there is a lot
and
of...
if I may, just as a follow-up question, what do you think about combining this with trusted execution environments in scenarios where I would, let's say that you have your precious data, that is maybe regulated, maybe it's a healthcare data or governmental data, and so you cannot put it in some centralized, powerful cloud or some cloud that I own. But I'm AI company and I have my algorithm in which I invested millions to train it. I don't want you to see my algorithm, but I need to send it to the edge in your data premises where your regulated data cannot leave. So okay, I'm sending my algorithm, but I want confirmations and attestations that my algorithm is protected, and maybe this can be done through the let's say, trusted execution environments. So we are combining federated learning and trusted execution environments.
Okay, so big question.
Yes.
All in all, from first hand, we work in healthcare sector beyond the other sectors, and having in mind when you use the homomorphic encryption that you work with binary numbers. I mean, it's not like working with elaborative data that you can work more extensive models. And for medicine, there is a lot of nice round numbers. Something even using float instead of integer is a problem because you change the algorithms, everything went wild. But to some extent, medicine is a good example. We have these sleep medicine use cases where we exchange the data between different countries. So medicine center in Berlin, in Paris, is exchanging data using these algorithms. And it works great until the data set becomes a lot of expensive for the computation. And I think at some point investments and the decisions should be made around that, because if you want to be carbon neutral from one point, or you wanted to protect the data from the other side. So not to go and derive from the topic, I would say this federated learning and homomorphic encryption are married somehow in a marriage that maybe not necessarily they go together. Homomorphic encryption is more for the centralized data. Federated distributed is something that is, from multiple endpoints that you collect and work maybe centralized. So in this wild marriage, I think something can be fruitful and we can get some nice use cases, but it doesn't work in all use cases well. We realized for the sleep, for the medicine in general, it can be used. When you have these simple statistics that they need to compute between different centers, it works pretty well. And what is missing is basically the second question you ask about trusted execution environment, because okay, we have the algorithm, we have the platform, but who guarantees that what you put is, again, secure, someone doesn't provide a bigger mess, then okay, you protected the data, but what happens from the bigger side, the overall picture, because it's not a trusted environment. So
maybe in a scenario where I use trusted execution environments in order to leverage the resources of the cloud, then it's okay because I have my algorithm and my data and some guarantees that this is protected from the cloud provider. But when we want to use it for data sharing, then it's a bigger challenge, I guess. Because if somebody else is providing algorithm, then probably I cannot trust that part.
Yeah.
Even though we protect it from the cloud provider.
Yeah, I can conform to that. I think we easily can rename this to AI Summit now. but of course, security is around the data.
Yes.
Security is around the data.
What I wanted to talk is really about the security, and here we are talking mostly about the privacy aspect of it, because this was a big focus, especially on the let's say with how should I say, with AI being a buzzword today, of course. But I wanted to use it also to kind of touch on the technical capabilities and technologies that we have today at our disposal in order to protect not only AI algorithms, but any kind of execution and any kind of protection of data in use. Because if we can do it for big and heavy algorithms, we can surely do it for some smaller, analytics. But talking about, the technologies and the trusted execution environments, for example, or execution, like offloading the execution to the cloud, then some kind of attestations are important so that we can get this trust. So Shushu, what you've been working with those kind of attestations, so how does it actually work, and what the capabilities do those trusted execution environments have in order so that we have trust in using those?
Well, I have guessed. So what you're asking is how the user management or
for example, or also,
secure. As I remember, normally the user has to register themselves with and then get the key from the trusted secure environment, and based on this key, which is hardware to the container, then you can somehow verify you are the really owner of this container and have access to the inside or something like that. And to the security channel between them is mostly called like a remote attestation. And it's quite developed, and I think more works now has come into also like the orchestration and attestation between containers somehow, but I'm not really expert on that piece. So maybe someone could help with that topic.
Anyone wants to say something about cryptographic attestation? Oh, okay. Maybe also one question about the usage or building a new tools. Again, maybe that are AI-based security tools, maybe, or for the monitoring of network or other monitoring tools. I would like to maybe ask you, Engin, what do you think about the development of monitoring and reporting, and also maybe automating this network monitoring or even threat mitigation through maybe through AI or some other automation procedures?
Yeah. Yeah, I mean, I also showed in the slides, like we had kind of like AI model, like training and inference. I mean, this is not like this, of course. There is a bigger picture that somehow needs to be on monitoring, and is one aspect. Like management of data is another aspect, and visualization of this kind of other aspects. So I think the tools are there. I mean, more or less, when you investigate like how you can build this pipeline in data engineering. But yeah, I mean, there is also, of course, security that you can add security to this kind of tools with the connections and somehow ensuring the data at rest is encrypted. So, but it depends on the scenario, right? So if you want to somehow because the security comes with the cost, and somehow you need to optimize your system based on what you get. If you are somehow, I don't know, dealing with some dummy servers, which maybe you could try to reduce the security level so that maybe you can get more benefit in terms of performance. But I see many tools in the system ecosystem to help you to monitor the data, to analyze it, to somehow ingest it, and they also come with kind of like security add-ons on top of it, because they are the tools that are always used in the production system. So, for example, if you are going to use Spark or this kind of tools that you want to, I don't know, analyze the data, I don't know, you want to do intrusion detection, this kind of things, they also come with the security add-on, but I think you need to optimize your system at the end of the day.
Okay, and maybe just to finish this panel discussion with far edge, you know, and we mentioned heterogeneity of the future 6G devices. So just from my curiosity, Nenad, you said you're edge guy. Do you see the proliferation of open source and in general open hardware architectures like RISC-V in the IoT networks, especially related to that, to let's say a strong push also from the EU Commission for the sovereignty and capabilities of Europe to produce and design hardware as well?
Yeah, I think this is getting bigger noticed these days. So not only Europe, but I think a lot of things are coming from Asia, running on the open source architecture made in Europe. And there is a lot of effort from the EU Commission these days with new tenders that are directly revolving around RISC-V. And people are getting more aware of the power, of course. I mean, if you look from the perspective of the personal computers, you have Windows, but also you have Linux on the other side that is more usable. You can do everything with it. You can accommodate it with for mobile phones, for whatever you want yourself. This is the same with the open source architecture for hardware, for processor. With that, I think it can even evolve and to some extent go beyond what we have commercially available today. And it is noticeable. Yeah. And I'm not sure how much, I didn't check the stats, how much commercial stuff is running on RISC-V at this moment, but in the USA, there's a lot of companies working and providing products that is running open source architectures. That is, I mean, not only usual use cases, but even mission critical use cases. So cars running on those. Yeah. So it's getting big.
Yeah. And Luis, speaking about this also, do you see that as a potential for like building new types of or accelerators much more easily when we have hardware at open source disposal, and also when we talk about open source, what about those frameworks for federated machine learning like Flower and others? What do you think about this like ecosystem? Is it good enough for like being used in production?
I think so. I think that there has been very important efforts from the community to make this open source frameworks work. One success case to me is Flower. I think it's being adopted more and more, perhaps at the beginning more by the research community, but we see a lot of potential in this type of frameworks, perhaps to be utilized in the future for commercial deployments. It's the same for the frameworks that you can find with PyTorch or TensorFlow, not only in federated learning, but if you start looking into the things they're doing for machine learning on the edge, I think that those are the reference frameworks or the reference tools that people use in practice to do the implementation. So I believe that is a critical component. Now everybody uses Python with PyTorch, TensorFlow to run things on a GPU. If you're not using that, perhaps you are a bit away from the market and the things that the people are doing in practice.
Yes, and of course maybe also TinyML on the microcontrollers that are also in cars or something like this. That is also.
And it's pretty impressive the things that we've seen in that scope. And I would like to see also how we evolve with generative AI and large language models applied to machine learning on the edge.
In the embedded devices, right? That are.
Yeah. Perhaps we're a bit early, but I'm sure that we will see very interesting things coming in the next months or in the next few years.
Yeah. Thanks.
So Josh, we're just running into 4 o'clock. So
exactly, I wanted to
all right,
conclude and to say first of all, thank all the panelists. I don't know if we have some more time for Q&A from the audience if somebody is interested. But just to summarize,
Hello. We're here today just to interrupt briefly. We're aware that there are people here who are here in good faith.
join the other discussion panel too. But of course, we are respectful to everything that's happening. So thank you so much. If there's any questions, we can take it by the coffee. The guys here were sitting down for an hour, so I'm sure everyone is tired. But yeah, see you tomorrow. Thank you so much, and I'm sure see you next year as well. So you have a question?
No, I wanted to ask a question related to our project.
Oh yeah, do you want to grab the guys, like, take the coffee break? Okay. Okay.